Hey everyone, welcome to the channel. Sit back, relax, and let your curiosity take over. Tonight, we're diving into 300 fascinating things about science. The facts, discoveries, and oddities that remind us just how mysterious our universe really is. From the tiniest quantum particles to the edges of the cosmos, from the chemistry of love to the biology of life, each chapter explores the strange beauty of how everything works. So take a deep breath, dim the lights, and get ready to wander through the astonishing world of science, where every answer leads to 10 more questions. Physics is the quiet language of the universe, the code behind every falling leaf, every star that burns, and every breath we take. It's both the simplest and the most profound science, asking questions so vast they almost sound poetic. What is motion? Why does time flow forward? What holds the cosmos together? For centuries, humans have tried to decode these mysteries, and though we've come far, physics keeps reminding us that the more we learn, the less we truly know. One of the first hidden wonders of physics lies in gravity, the invisible hand that shapes galaxies, moons, and your morning cup of coffee. Most of us think of gravity as a simple downward pull, but it's far more elegant than that. According to Albert Einstein's theory of general relativity, gravity isn't a force in the traditional sense. It's the curvature of space-time itself. Imagine placing a bowling ball on a trampoline. The fabric bends, and any smaller object nearby naturally rolls toward it. That's gravity, not a pull, but a gentle dip in the geometry of existence. Every planet, star, and black hole creates these curves, and together they choreograph the cosmic dance we call reality. But gravity has secrets. It's the weakest of the 4 fundamental forces, yet it controls everything massive. You can lift a paperclip with a magnet, defying the entire gravitational pull of the Earth, and yet gravity governs galaxies spanning millions of light years. Why it's so weak, or why it exists at all, remains one of physics' biggest puzzles. Some scientists suspect gravity may leak into extra dimensions, unseen layers of reality that exist beyond our 3-dimensional world. Then there's light, the fastest, most mysterious traveler in the universe. Light behaves both like a wave and a particle, a duality that has puzzled scientists since the 1600s. Sometimes it ripples through space like energy. Other times, it acts as tiny packets called photons. Even stranger, photons have no mass, yet they carry momentum, and they always move at the same speed. 299,792,458 meters per second. No matter how fast you chase light, it never slows down. This constancy is what gave rise to Einstein's most famous equation, E equals mc squared, showing that energy and matter are 2 sides of the same cosmic coin. But what happens when light bends? That's where physics crosses into magic. Gravitational lensing, predicted by Einstein and confirmed a century later, occurs when light from a distant galaxy bends around another massive object, like a black hole on its way to Earth. It's space-time itself acting as a cosmic magnifying glass, allowing astronomers to see galaxies billions of years old. Every time we peer through one of these lenses, we're literally looking into the past. Speaking of black holes, they're perhaps the most mesmerizing wonders of all. A black hole forms when a massive star collapses under its own gravity, crushing matter into a point so dense that not even light can escape. Around it lies the event horizon, a one-way border where time itself slows to a crawl. To an outside observer, an object falling into a black hole appears frozen forever at the edge, its image red-shifting into darkness. But from the falling object's perspective, it crosses the horizon effortlessly. A silent, cosmic contradiction where two realities coexist. And yet, black holes aren't just cosmic destroyers. They may also be gateways to understanding quantum gravity, the elusive bridge between Einstein's relativity and the strange world of quantum mechanics. Inside their depths, the known laws of physics break down, hinting that space and time might not be continuous, but quantized, made of discrete pixels of reality. Physicists like Stephen Hawking proposed that black holes actually emit radiation, now known as Hawking radiation, suggesting they can shrink and evaporate over time. If true, even the darkest corners of the universe aren't eternal. But gravity and light are only part of the story. The universe runs on four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. The strong force binds protons and neutrons in atomic nuclei. The weak force governs radioactive decay. Electromagnetism powers everything from lightning to Wi-Fi. And gravity keeps the cosmos in motion. These four forces, working in balance, create everything we see, from the hydrogen in your blood to the stars in Andromeda. And physicists have spent decades trying to unify them under one elegant framework: the long-sought theory of everything. Some believe that theory lies in string theory, which suggests that all particles are actually tiny, vibrating strings of energy. Their different vibrations give rise to the properties we perceive: mass, charge, spin. It's a breathtaking idea that the universe, at its core, is made of music. Each atom, each photon, each heartbeat, all are different notes played by the same cosmic instrument. Others look toward quantum field theory, where the universe isn't filled with particles, but with invisible energy fields. What we call particles are just localized excitations, ripples in these fields. You, me, the stars, and the vacuum of space all share the same fabric. The universe isn't a collection of things, but a single, unified field of vibration. And then there's the biggest mystery of all: dark matter and dark energy. According to modern astrophysics, everything we can see, stars, planets, gas, galaxies, makes up only about 5% of the universe. The other 95% is completely invisible. Dark matter acts like scaffolding, holding galaxies together with unseen gravity, while dark energy drives the universe's expansion, pushing everything farther apart. We don't know what either of them actually is, but without them, the cosmos as we know it wouldn't exist. Physics doesn't just explain the universe, it re-enchants it. Every law reveals not certainty, but mystery layered beneath mystery. The apple that fell on Newton's head wasn't just a clue about gravity. It was an invitation to glimpse the invisible web that connects all things. From quantum particles to black holes, physics tells us that the universe isn't a cold machine, but a living equation, dynamic, interwoven, and still unfolding. Somewhere between the forces that bind atoms and the energy that fuels galaxies, there's a quiet truth. We're part of the equation too. The same laws that move stars also move your heartbeat. The same constants that shaped the Big Bang govern the spark in your brain when you wonder about it. And maybe that's the most beautiful thing about physics. It doesn't just describe the universe, it describes us. Beautiful and bizarre, those rules become. At its heart, the universe runs on symmetry. Imagine folding a snowflake in half and seeing it perfectly match on both sides. That's symmetry, and it's the foundation of every physical law. Whether it's the motion of planets or the flow of electricity, symmetry gives nature consistency. But here's the twist. The universe also breaks symmetry. just enough to make life possible. In the early moments after the Big Bang, for example, matter and antimatter were created in equal amounts. But for reasons we still don't fully understand, there was a tiny imbalance. Just one extra particle of matter for every billion of antimatter. That tiny mistake is why anything exists at all. If the universe were perfectly symmetrical, you wouldn't be here reading this. The universe also obeys a strange sense of economy, known as the laws of conservation. Energy cannot be created or destroyed. It only changes form. The heat from your morning coffee was once sunlight, the atoms in your body were once stardust, and the energy in your heartbeat may one day power the orbit of another world. Everything transforms, but nothing truly disappears. Even when a star dies in a supernova, its matter and energy simply spread out, recycled into new suns, new planets, new life. In that way, physics quietly promises immortality, not for individuals, but for everything that ever was. And yet, amid this cosmic order, physics reveals a strange truth. Chaos is essential. The universe thrives on randomness. Quantum mechanics shows that at the smallest scales, particles don't follow neat, predictable paths. Instead, they exist in clouds of probability, moving in ways no equation can fully predict. This uncertainty, called Heisenberg's uncertainty principle, isn't a flaw, it's a feature. Without it, electrons couldn't form stable orbits, chemistry couldn't exist, and life's complexity would vanish. Paradoxically, it's the unpredictability of the quantum world that gives rise to the structure of everything larger. One of the most astonishing invisible rules is entropy, the law of disorder. According to the second law of thermodynamics, everything in the universe tends toward chaos. Heat spreads out, systems decay, and order inevitably breaks down. Left unchecked, entropy will one day claim even the stars, leaving behind a silent cosmos of scattered particles and fading light. This future, known as the heat death of the universe, might sound bleak, but entropy is also what makes existence dynamic. Stars burn because they convert energy from order to disorder. Living beings exist because they resist entropy, maintaining internal order in an ever-declining universe. Life itself is rebellion against decay. If entropy is the universe's whisper toward chaos, time is its rhythm. But time, too, is stranger than it seems. Einstein showed that time is not absolute. It bends and stretches with motion and gravity. The faster you move, the slower time flows for you. Clocks near massive objects like black holes tick more slowly than those far away. Astronauts orbiting Earth experience time slightly differently than those on the ground, measurable proof that time is not universal but personal. The idea that now depends on where you stand rewrote our understanding of existence itself. At the cosmic level, these laws intertwine in elegant ways. The speed of light, for example, is not just a number. It's the ultimate speed limit of the universe, and it dictates how space and time themselves behave. If you approach the speed of light, distances shrink and time slows until, theoretically, at light speed, both vanish entirely. To a photon, there's no distance or time between its emission from a star and its arrival at your eye. For light, the entire universe happens at once. That's where physics starts to sound almost philosophical. The universe isn't just a collection of moving parts. It's a living equation where space, time, energy and matter constantly transform into one another. It's all one fabric, stretching and rippling in response to what happens within it. When a planet orbits a star, it's not being pulled by some invisible string. It's simply following the natural curves of space-time. When two electrons repel each other, they're exchanging virtual photons, ripples of energy that momentarily exist just long enough to carry information. The smallest interactions echo across the largest scales. Even at the tiniest level, nature obeys hidden patterns. One of the most beautiful is wave-particle duality, the idea that everything, even you, has both particle-like and wave-like properties. The boundary between energy and matter is fluid. That means every atom in your body has a wavelength, every electron a vibration. The universe is not made of solid things, but of oscillations, music made visible. Physicist Richard Feynman once said, "Everything is made of waves of the same stuff." It's a poetic truth that turns physics into a kind of cosmic art. There's also a quiet rule about how the universe remembers itself, a principle known as information conservation. Even when matter falls into a black hole, seemingly erased from existence, many physicists now believe that information about it still lingers, encoded in faint radiation at the event horizon. In this view, the universe never truly forgets. Every event leaves a trace, every particle a memory. Reality itself may be a kind of cosmic database, continually updating but never deleting. All these laws, from entropy to relativity, point toward a universe that's not chaotic, but profoundly self-consistent. Every atom, every beam of light, every planet follows the same rulebook, no exceptions. Yet, within that order lies infinite creativity. Out of the same few constants, gravity, electromagnetism, nuclear forces, nature builds galaxies, mountains, oceans, and minds capable of wondering about it all. The invisible rules of physics don't limit the universe, they allow it to exist. Without them, stars wouldn't shine, molecules couldn't bond, and time itself might unravel. They're not shackles, they're the grammar of reality, giving structure to chaos and meaning to motion. Perhaps that's what makes physics so awe-inspiring. It's not about memorizing equations or constants, but about glimpsing the invisible architecture behind everything. When you look at a rainbow, you're seeing sunlight refracted by droplets following Snell's law. When you hear music, you're hearing air molecules vibrating in harmonic frequencies predicted by wave physics. Every moment of wonder is really a quiet conversation between you and the universe's rules. And yet, those rules don't make the universe predictable. They make it alive. Beneath the formulas and theories lies something timeless, balance, beauty, and the mystery of existence itself. The more we uncover, the clearer it becomes that physics isn't just about how the universe works. It's about why it feels so endlessly fascinating. Imagine a world where objects can be in two places at once, where particles blink in and out of existence, where observation itself decides what's real. This isn't science fiction, it's quantum mechanics, the branch of physics that governs the smallest scales of reality. It's the science that underpins everything from the glow of your phone screen to the reactions inside your cells. Yet it's so bizarre that even the scientists who discovered it admitted they didn't fully understand it. At its core, quantum mechanics is the study of the universe at the level of atoms and subatomic particles, electrons, photons, quarks, and other building blocks of matter. But unlike the predictable world we see every day, the quantum world operates under rules that defy common sense. In this strange realm, certainty disappears, replaced by probabilities, possibilities, and paradoxes. The story begins in the early 20th century, when physicists were trying to explain why light emitted by hot objects, like stars or light bulbs, had specific colors or spectra. Classical physics couldn't explain it. That's when Max Planck proposed something revolutionary. Energy isn't continuous, but comes in tiny, discrete packets called quanta. It was a quiet idea that shattered centuries of scientific thought. The universe, it turned out, doesn't flow smoothly, but ticks in tiny, indivisible steps. A few years later, Albert Einstein expanded this idea by explaining the photoelectric effect, how light can knock electrons off metal surfaces. He showed that light behaves not just as a wave, but as individual particles, photons, each carrying a specific quantum of energy. This dual nature of light, both wave and particle, would become one of the cornerstones of quantum theory. Then came Niels Bohr, who introduced the model of the atom as a miniature solar system, with electrons orbiting the nucleus at fixed energy levels. But the deeper scientists looked, the stranger things got. Electrons didn't behave like tiny planets. They acted like clouds of probability existing everywhere at once until measured. When you observe an electron, it suddenly chooses a position, collapsing from a wave of possibilities into a single outcome. This idea, that observation determines reality, is one of the most mind-bending concepts in science. It's vividly demonstrated in the famous double-slit experiment. When scientists shoot particles like electrons through two narrow slits onto a screen, they create an interference pattern, proof that each particle behaves like a wave going through both slits simultaneously. But when scientists try to observe which slit the electron goes through, the interference pattern vanishes. The particles behave like solid objects instead. Simply watching them changes the outcome. This phenomenon, called the observer effect, raises deep questions. Does reality exist independently of observation? Or does the act of measurement bring it into being? Some physicists argue that the universe itself behaves like a cosmic experiment, reality crystallizing only when observed. Others suggest that every possible outcome happens simultaneously in branching timelines, the many worlds interpretation, where every quantum event splits the universe into countless versions of itself. One of the strangest features of quantum mechanics is entanglement. When two particles become so deeply connected that the state of one instantly determines the state of the other, no matter how far apart they are. Einstein called it spooky action at a distance, but modern experiments have proven it real. Two entangled photons can remain linked across vast distances, reacting instantly to changes in each other. It's as if they share a hidden communication channel beyond space and time. This defies our everyday understanding of cause and effect, but it's not just a curiosity. It's the foundation of quantum computing and quantum teleportation. In 2017, scientists in China teleported the quantum state of a photon from Earth to a satellite orbiting hundreds of kilometers above. Information, entangled at the quantum level, transcended distance in a way classical physics cannot explain. At the mathematical heart of quantum mechanics lies the wave function, represented by the Greek letter psi. It's an equation that describes all possible states of a system. But the wave function doesn't tell you what is, only what could be. It's a map of probabilities, collapsing into a single outcome when measured. That collapse, known as the Copenhagen interpretation, remains one of the biggest mysteries in science. Why does observation cause a change? What counts as an observer? Is it consciousness itself? Physicist Erwin Schrödinger famously illustrated the absurdity of this with his thought experiment, Schrödinger's cat. Imagine a sealed box containing a cat, a radioactive atom, and a poison mechanism triggered if the atom decays. According to quantum mechanics, until you open the box and observe it, the atom is both decayed and undecayed, meaning the cat is both alive and dead at the same time. Only when you look does the cat choose a state. It's a haunting metaphor for how the quantum world may function, reality suspended between possibilities until observation forces a decision. But quantum mechanics isn't just weird, it's astonishingly accurate. Its predictions have been tested to more than a dozen decimal places. It explains how atoms bond, why stars shine, and how semiconductors work. The entire digital age, computers, lasers, smartphones, and even MRI machines, exists because quantum mechanics is true. We live in a world powered by the rules of uncertainty, and those rules reveal something profound about existence. Beneath all the chaos and unpredictability lies a deep order, a quantum harmony that connects everything. Particles pop into and out of existence in the quantum vacuum, yet the total energy always balances to zero. Virtual particles borrow energy from the universe for an instant, only to return it. Every interaction obeys conservation, every fluctuation leaves the cosmos unchanged in total. It's as if the universe is a perfect accountant of its own chaos. Quantum theory even touches philosophy and spirituality. Some thinkers see it as evidence that consciousness might play a role in shaping the physical world. Others see it as proof of the universe's inherent mystery, that reality, at its deepest level, can never be fully known, only approximated. As physicist Richard Feynman once said, "If you think you understand quantum mechanics, you don't understand quantum mechanics." It's not a flaw in our comprehension. It's a reminder that reality is richer, stranger, and more intricate than logic can contain. In the end, quantum mechanics isn't just a theory, it's a mirror reflecting our own curiosity. It shows that the universe isn't a machine ticking predictably in the dark, but a living field of potential, waiting to be seen, waiting to be known. And perhaps, like the electron in the double-slit experiment, the universe itself becomes real only when we look at it. When most people hear quantum mechanics, they imagine futuristic labs, equations written on glowing chalkboards, and scientists in white coats tinkering with strange devices. But what few realize is that quantum physics isn't confined to laboratories. It's everywhere, shaping our daily lives in ways we rarely notice. Every time you turn on a light, use your phone, or even think a thought, you're participating in a world governed by the tiniest, strangest laws in existence. The quantum realm isn't just theoretical, it's the invisible foundation of modern life. Take the sunlight streaming through your window. The warmth on your skin is the result of nuclear fusion, a quantum process happening in the heart of our sun. Deep inside, hydrogen atoms collide under immense pressure, but they shouldn't merge easily. According to classical physics, their positively charged nuclei should repel each other. Yet thanks to a quantum trick called tunneling, particles can borrow energy to pass through barriers they otherwise couldn't cross. Without this quantum quirk, the sun would never shine, and life on Earth would be impossible. Every sunrise, every breath of oxygen is a gift from quantum mechanics. Quantum tunneling doesn't just power stars, it powers technology. Flash memory, used in phones and USB drives, relies on electrons tunneling through thin insulating layers to store data. It's the same principle that keeps our digital world running. Even in medical imaging, quantum effects are at play. MRI machines work by detecting how atomic nuclei in your body align and spin when exposed to magnetic fields. These tiny spins, described by quantum physics, help doctors see inside the human body without surgery. Then there's semiconductors, the backbone of every computer, phone, and smart device. Transistors, the microscopic switches that make up computer chips, rely on quantum mechanics to control the flow of electrons. When you type a message or scroll through a feed, billions of transistors are opening and closing in patterns dictated by quantum principles. The digital age isn't just built on technology. It's built on quantum understanding. Even the color of objects depends on quantum physics. When light hits a surface, atoms absorb or reflect photons based on their energy levels. Electrons inside atoms can only occupy specific energy states, and when they jump between them, they absorb or emit light of particular wavelengths. That's why leaves are green, the sky is blue, and sunsets glow red. Every shade of nature is painted by the quantum choreography of electrons. But the quantum world doesn't stop at technology or color. It's woven into life itself. Inside your cells, molecules perform reactions that depend on quantum behavior. Photosynthesis, for example, the process that lets plants turn sunlight into energy, operates at near-perfect efficiency because of quantum coherence. Photons absorbed by chlorophyll don't take random paths. They explore multiple routes simultaneously, just like particles in the double-slit experiment, and choose the most efficient one. Nature has been using quantum computing billions of years before humans even conceived of it. Even your sense of smell may depend on quantum mechanics. One theory suggests that our noses don't simply detect the shape of molecules, but their vibrations, the frequencies of their atomic bonds. That's a quantum-level process where electrons tunnel and interact with molecules to produce distinct sensory responses. If true, every breath you take is a tiny quantum measurement. Your brain, too, may owe some of its complexity to quantum effects. While neuroscience doesn't yet claim that consciousness is purely quantum, some researchers, like physicist Roger Penrose, believe that microtubules within neurons could use quantum coherence to process information beyond classical limits. The idea is controversial but fascinating, that the very act of thought might involve the same physics that governs the universe's smallest particles. Quantum physics also underlies lasers, which are used in everything from barcode scanners to eye surgery. A laser works by stimulating atoms to emit photons in sync, a process called stimulated emission, first described by Einstein in 1917. The result is a beam of perfectly aligned light waves, coherent and powerful. Without this quantum insight, modern communication, fiber optics, internet connections, even Blu-ray players would not exist. And if you've ever used GPS navigation, you've depended on quantum mechanics more directly than you might think. The atomic clocks aboard GPS satellites measure time with extreme precision using the oscillations of atoms like cesium. These oscillations are quantum events, transitions between discrete energy states. Without that accuracy, your GPS would drift by kilometers each day. Quantum physics literally keeps us from getting lost. Even something as simple as metal shining or glass being transparent can be traced to the quantum world. In metals, electrons move freely in energy bands, allowing them to reflect light and conduct electricity. In glass, electrons are bound tightly in atoms, meaning they can't absorb visible light, and so it passes through. The everyday materials we take for granted behave the way they do because of the quantum architecture of their atoms. And soon, quantum mechanics will shape the future even more dramatically. Scientists are developing quantum computers which use qubits instead of traditional bits. Unlike bits that can be either 0 or 1, qubits can exist as both simultaneously thanks to superposition. When entangled, multiple qubits can perform complex calculations exponentially faster than classical computers. Tasks that would take centuries for today's supercomputers, like simulating molecules or cracking encryption, could take seconds on a quantum machine. We stand at the dawn of a technological revolution powered by quantum laws older than the stars themselves. Another emerging field is quantum cryptography, where communication systems are protected by the laws of physics rather than passwords. Because observation changes quantum states, any attempt to eavesdrop on a quantum message immediately reveals itself. This could make future networks unhackable, securing everything from financial data to government transmissions. And let's not forget quantum teleportation. Not the science fiction kind that moves people through space, but the real transfer of quantum information. Scientists have already teleported quantum states between particles separated by kilometers and even between Earth and orbiting satellites. While we're far from teleporting humans, the principles discovered here are building the backbone of the quantum internet, a network that could link computers and sensors across the globe with unprecedented speed and security. What's remarkable is that all these astonishing feats, from photosynthesis to computing, arise from rules that seem almost magical. The quantum world is built on uncertainty, and yet it gives rise to the most reliable technologies we've ever created. It's as though nature wrote its own paradox. The more unpredictable the microscopic world becomes, the more predictable the macroscopic one feels. Every glance at your phone, every ray of light, every electric current is a quiet reminder of this invisible order. Beneath the surface of everything we know hums a realm of endless possibility, a place where matter is music and reality dances to the rhythm of probability. Quantum mechanics doesn't just describe that world, it connects us to it. We are made of atoms that obey its rules, powered by stars born of its mysteries, and guided by devices that whisper its secrets. The universe may be vast, but its smallest particles carry the same message everywhere. The ordinary is always extraordinary, if you look closely enough. The human brain, a 3-pound universe wrapped in bone, is perhaps the most complex structure known to science. It's the seat of thought, memory, emotion, and imagination. Every idea, every heartbeat, every dream you've ever had began as an electrical whisper inside this grey labyrinth. Scientists can map galaxies and split atoms, yet the organ that makes all of that possible remains one of the deepest mysteries in the cosmos. At its simplest description, the brain is a network of roughly 86 billion neurons, each connected to thousands of others through tiny junctions called synapses. These neurons don't communicate with words or wires, but with electrical impulses and chemical signals, flashes of voltage that travel faster than thought. When you see a sunset, solve a problem, or recall a childhood song, billions of neurons fire in intricate patterns, forming what we experience as consciousness. But for all our progress, scientists still don't fully understand how those electrical signals translate into subjective experience, what philosophers call the hard problem of consciousness. We can observe which areas of the brain light up when someone feels fear or joy, yet we can't explain why those patterns produce the feeling itself. The gap between matter and mind remains a mystery that even physics can't bridge. One of the brain's greatest secrets is plasticity, its ability to change and rewire itself throughout life. For centuries, researchers believed the brain's structure was fixed after childhood. But modern neuroscience has proven the opposite. Every experience, every skill you learn, even every thought you repeat, reshapes your neural connections. London taxi drivers, for example, have been shown to develop larger hippocampi, the brain region responsible for navigation, after years of memorizing city maps. It's proof that the mind literally sculpts itself through effort and experience. This adaptability is what allows people to recover from brain injuries, learn new languages, and adapt to change. It's also what underlies habits, both good and bad. Repetition strengthens neural pathways, making certain actions easier over time. That's why mastering an instrument, forming a routine, or even changing your mindset isn't magic. It's physics and chemistry at work. Then there's the unconscious mind, the vast territory beneath awareness. Studies show that up to 95% of our decisions happen below the level of conscious thought. Before you decide to move, speak, or even reach for a cup of coffee, your brain has already begun the process. In other words, free will might not be as free as we think. Our conscious mind often arrives late to decisions our subconscious has already made. Yet the unconscious isn't just a machine running background processes. It's also where creativity and intuition live. The aha moment, when a solution suddenly clicks, often comes after you stop actively thinking about the problem. That's because your brain continues processing in the background, connecting patterns your conscious mind overlooks. Some of history's greatest insights, from Einstein's thought experiments to artistic breakthroughs, emerged not from logic, but from this quiet, unseen side of the mind. The brain's communication system is also deeply chemical. Neurotransmitters like dopamine, serotonin, and oxytocin act as emotional messengers. Dopamine fuels motivation and reward, making us chase goals. Serotonin stabilizes mood. Oxytocin fosters trust and connection, especially during touch or bonding moments. Together, they create the emotional symphony that colors human experience. Every feeling you've ever had, love, anxiety, joy, heartbreak, is, at its core, a carefully tuned chemical cascade. Sleep, too, remains one of the brain's most essential and mysterious functions. During deep sleep, your brain consolidates memories, repairs neurons, and even clears out toxic waste through a system called the glymphatic network. In REM sleep, your brain enters a creative frenzy, generating dreams that blend memories, fears, and imagination. Scientists believe dreams may help the brain solve problems or simulate threats, a kind of overnight rehearsal for reality. In that sense, dreaming isn't just fantasy, it's mental maintenance. And then there's the split brain phenomenon, one of neuroscience's most fascinating discoveries. The brain's two hemispheres, left and right, are connected by a bundle of fibers called the corpus callosum. In rare medical cases where this bridge is severed to treat epilepsy, each hemisphere continues to function independently. The result? Two minds in one body. One hand might button a shirt, while the other unbuttons it. The right hemisphere may recognize a face that the left cannot name. These cases revealed that consciousness isn't singular but distributed, a cooperation between many selves that together feel like you. Even more astonishing is how the brain constructs reality itself. What you see, hear, and feel are not direct experiences of the world, but interpretations your brain creates based on sensory input. Light enters your eyes, sound waves hit your ears, and electrical signals travel to the brain, where they're stitched together into a seamless picture. But that picture is subjective. Optical illusions, hallucinations, and memory errors show that the brain can be fooled, that reality, in a way, is a controlled hallucination guided by consensus. And memory, our most trusted sense of identity, is among the most unreliable. Every time you recall an event, your brain slightly rewrites it. Neurons refire, connections shift, and details subtly change. Over years, your memories evolve, not like a photograph, but like a story retold. That's why eyewitness testimonies vary. why nostalgia feels dreamlike, and why our pasts are more fluid than we realize. The brain isn't a storage device. It's a storyteller, constantly editing and refining its own narrative. Despite all this, the brain operates on astonishing efficiency. It runs on about 20 watts of power, roughly the energy of a dim light bulb. Yet within that limited energy, it performs trillions of operations per second, far surpassing the most advanced supercomputers in adaptability and learning. It encodes language, invents art, builds civilization, and questions its own existence, all while consuming less power than your laptop. But perhaps the most awe-inspiring thing about the human brain is that it's self-aware. Out of raw matter, evolution sculpted an organ capable of asking, "Who am I?" No other structure in the known universe does that. Your brain not only observes the cosmos, it reflects it. The same atoms that once burned in stars now think, dream, and remember. Consciousness, in that sense, is the universe becoming aware of itself. And though neuroscience has mapped much of the brain's terrain, its deepest secret, how it produces the experience of being alive, remains unsolved. Some scientists believe it's a byproduct of complexity, an emergent property that arises when enough neurons interact. Others think consciousness may be a fundamental feature of the universe itself, woven into the fabric of space and time. Whatever the answer, the search for it continues, in labs, in philosophy, and within ourselves. In the end, the brain isn't just an organ. It's an explorer, an artist, a scientist, and a dreamer, all at once. It builds worlds, questions them, and rebuilds them again. The deeper we study it, the more we realize that understanding the brain isn't just about decoding biology. It's about uncovering what it means to be human, to feel, to wonder, and to know that we know. The mind is the unseen frontier, a realm where thoughts shape reality, where emotion becomes energy, and where imagination bends the limits of what we think is possible. While the brain is a physical organ, the mind is its intangible counterpart. The vast, silent landscape where memories live, ideas collide, and identity takes form. Scientists have mapped every region of the brain, but the mind, the thing that feels, remains elusive. It's both the product of biology and something greater, the spark that turns a cluster of neurons into a conscious being. One of the mind's greatest mysteries is its ability to create perception. Every moment, billions of bits of information flood your senses, sounds, lights, textures, smells. Yet, your mind filters almost all of it out, focusing only on what it deems important. This selective focus is called attention, and it's the reason you can hear one voice in a crowded room or ignore the ticking of a clock you've heard for hours. It's also deeply fragile. Every distraction you encounter chips away at it. Modern neuroscience shows that multitasking isn't real. The brain simply switches tasks rapidly, losing focus each time. The mind thrives not in chaos, but in stillness. Stillness, however, reveals another hidden power: imagination. Unlike any other species, humans can picture things that don't yet exist. Entire worlds, inventions, futures. When you imagine something vividly enough, the same neural circuits fire as if you were actually experiencing it. In other words, the brain can't fully distinguish between thought and reality. That's why mental rehearsal, visualizing a skill or goal, genuinely improves performance. Olympic athletes, musicians, and even astronauts use visualization to enhance precision and confidence. The mind doesn't just observe the world, it builds it. This same mechanism is what gives rise to the placebo effect, one of science's most baffling phenomena. When patients believe they're receiving treatment, their symptoms often improve, even if they've only been given sugar pills. Studies show that belief alone can trigger measurable biological changes. Heart rates slow, pain diminishes, and stress hormones drop. The body listens to the mind. Expectation becomes biology. The placebo effect isn't deception. It's proof that perception can rewrite physiology. But the mind's influence runs deeper than healing. It also shapes emotion, the invisible current guiding every decision we make. Emotion isn't a weakness or distraction. It's intelligence in motion. Neuroscientists have discovered that without emotional input, humans struggle to make even the simplest choices. Our rational mind depends on feeling to assign value. When you choose a meal, a career, or a person to love, it's your emotional brain, the limbic system, that decides first. Logic merely justifies it afterward. Emotion also binds us to others through empathy, the ability to feel what someone else feels. When you see another person smile or cry, your brain activates mirror neurons that mimic their experience. This is why stories move us, why we cry at movies, why compassion feels instinctive. The mind, in essence, is not confined to the self. It reaches outward, connecting consciousnesses across invisible lines. Some scientists even theorize that empathy evolved as a survival mechanism, hardwiring cooperation into our species. The mind's adaptability is also what fuels resilience. Under trauma or loss, it has the power to rebuild itself through a process called neuroplastic recovery. The brain can reroute functions to new areas, helping people regain abilities once thought lost. This adaptability extends to mental health. Cognitive therapies work by reshaping the neural circuits tied to negative thinking. When you change how you think, you literally rewire your brain. The old saying, mind over matter, isn't just metaphor, it's measurable science. Another fascinating ability lies in the subconscious mind, the layer beneath awareness that controls breathing, habits, and intuition. It stores every experience you've ever had, processing information faster than your conscious mind could ever manage. That's why gut feelings often prove correct. They're your brain's pattern recognition system, drawing conclusions from data you didn't even realize you absorbed. Intuition, in that sense, isn't mystical. It's compressed wisdom. And yet, there's a dimension of the mind that science is only beginning to explore: the altered states of consciousness. Through meditation, sensory deprivation, psychedelics, or near-death experiences, people report profound shifts in perception, time, and self. Brain scans of deep meditative states show reduced activity in the default mode network, the region associated with the ego and self-referential thought. When it quiets down, people often describe feeling one with everything, a sense of unity that transcends individuality. Whether spiritual or neurological, these experiences hint at the mind's capacity to dissolve boundaries and connect with something larger. In recent decades, research into meditation and mindfulness has revealed measurable effects on the brain. Long-term practitioners show thicker regions in areas linked to attention and emotional regulation and reduced activity in stress-related circuits. Mindfulness doesn't erase thoughts. It changes the relationship to them. It teaches the mind to observe without judgment, turning chaos into calm. Even short daily practices can lower blood pressure, improve sleep, and enhance emotional clarity. The mind, it seems, is both the source of stress and its antidote. The mind also has a dark side, its ability to deceive itself. Cognitive biases, illusions, and false memories are all proof that the mind isn't a perfect instrument of truth. It interprets reality, not records it. Optical illusions show how the brain fills in missing information. Psychological illusions show how belief shapes perception. For instance, confirmation bias makes us notice only what supports our existing views, while hindsight bias convinces us we knew it all along. The mind constructs a comfortable version of the world, one that's coherent, even if not always accurate. Yet this self-deception may be part of evolution's genius. Optimism, even when unrealistic, helps us persist. Memory's flexibility allows forgiveness. The ability to imagine alternate realities fuels creativity. The mind's imperfections, rather than flaws, might be the very mechanisms that make growth and survival possible. As technology advances, scientists are finding ways to peek deeper into this mysterious engine. Brain-computer interfaces now allow paralyzed individuals to move robotic limbs using thought alone. Artificial intelligence trained on brain scans can reconstruct images people are viewing, or even approximate what they're imagining. These breakthroughs are blurring the line between mind and machine, hinting that one day consciousness itself might be mapped, replicated, or expanded beyond biology. But even as we approach these frontiers, one truth remains. The mind is not just neurons firing, it's experience itself, the movie playing in first-person perspective. We are the only creatures, as far as we know, who can reflect on their own awareness. When you look at a sunset and feel awe, when you remember someone you love, when you ask, "Who am I?" you're touching that mystery directly. In every era, science has tried to explain the mind as something mechanical, once as gears, then as circuits, now as data. But perhaps the true power of the mind lies in what can't be reduced, its ability to love, to imagine, to create meaning out of chaos. It's both scientist and subject, observer and observed. And maybe that's the greatest secret of all, that the universe built something capable of contemplating itself. The mind, with all its contradictions, isn't just a feature of the cosmos. It is the cosmos, awake and wondering, space and time. Two words that seem simple, yet they define everything we know. They are the invisible stage on which the universe performs its grand play. Every planet's orbit, every heartbeat, every flash of light happens within their fabric. But the more scientists study them, the stranger they become. Space isn't empty, and time isn't constant. They bend, stretch, and even warp, depending on where you are and how fast you're moving. In the vast theater of the cosmos, space and time aren't the backdrop, they're the actors. To understand their mystery, we have to go back to Albert Einstein's theory of relativity, the idea that shattered the rigid, clockwork universe of Newton. Before Einstein, physicists believed space and time were fixed, an absolute framework that everything existed within. But Einstein revealed they were intertwined into a single, flexible entity: space-time. Matter and energy don't just exist in space-time, they shape it. Massive objects like stars and planets warp the fabric around them, creating what we feel as gravity. Imagine a giant rubber sheet with a heavy ball in the center. The ball makes a dip, and smaller objects placed nearby roll toward it, not because they're being pulled, but because they're following the sheet's curvature. That's gravity in Einstein's universe, not a force, but the geometry of existence. The Earth doesn't fall into the sun because it's being pulled. It's simply moving along the curved path that space-time lays out for it. This bending of space also affects time. The stronger the gravity, the slower time flows. Clocks run more slowly on Earth's surface than on satellites orbiting above, a fact engineers must account for when designing GPS systems. Without correcting for the time dilation caused by gravity, GPS would drift by several kilometers every day. Your phone works because physics understands how time bends. Even stranger, motion itself warps time. According to special relativity, the faster you move, the slower time passes for you relative to someone standing still. This isn't a theoretical quirk. It's been proven with atomic clocks flown on airplanes and aboard spacecraft. Time dilation is real. It means that astronauts aboard the International Space Station experience time slightly slower than people on Earth. They are, quite literally, aging more slowly, by fractions of a second, but measurable ones nonetheless. This leads to one of the most mind-bending implications of relativity. Time is relative, not universal. There's no single now shared across the cosmos. For two observers moving differently through space-time, what counts as simultaneous can differ. Events that seem to happen at the same time for one person may occur in different orders for another. In a very real sense, every observer lives in their own version of the universe, their own personal timeline. But relativity doesn't just bend time, it also opens the door to time travel, at least theoretically. If you could travel at speeds close to that of light, your clock would slow dramatically compared to those back home. In one famous thought experiment, known as the twin paradox, one twin travels near light speed and returns to find their sibling much older. Time travel to the future, Einstein showed, is not only possible, it's built into the fabric of reality. Traveling to the past, however, is a different story. The laws of physics don't explicitly forbid it, but doing so could cause paradoxes, events where cause and effect collapse in on themselves. Some physicists believe that wormholes, theoretical tunnels through space-time, might offer a way around that. A wormhole could, in theory, connect two distant points in space, or two different times. But keeping one stable would require negative energy, a concept that for now exists only in equations. Still, the math suggests the universe may hide shortcuts, cosmic passageways linking distant stars or even eras. Time's mystery deepens when we look at the arrow of time. Why it always moves forward. The laws of physics work equally well backward and forward, yet we only experience one direction. The reason, scientists believe, lies in entropy, the natural tendency of systems to move from order to disorder. A cup of coffee cools, but never spontaneously heats itself. You can scramble an egg, but you can't unscramble it. Entropy increases with time, giving the universe its one-way flow, from simplicity to complexity, from birth to decay. But there's a haunting question hidden here. If the Big Bang started everything in a state of perfect order, where did that order come from? Why was the universe's entropy so low at the beginning? No one knows. Some physicists suspect that time itself may have emerged from that initial condition, that before the Big Bang, time as we know it didn't exist at all. The beginning of time, then, wasn't just the start of motion. It was the birth of change. Quantum physics complicates the picture even more. On the smallest scales, time may not be continuous. Some theories suggest it's made of discrete ticks, like frames in a movie. Others propose that time is an illusion altogether, a side effect of our perception, emerging from quantum entanglement and thermodynamics. In these views, the universe doesn't evolve through time. It simply is, a timeless web where all events exist simultaneously. Our sense of past, present, and future might just be how consciousness experiences that frozen geometry. Even space itself may not be what it seems. At cosmic scales, it stretches faster than the speed of light, carrying galaxies away from one another in the expansion of the universe. At microscopic scales, it bubbles with quantum fluctuations, tiny, spontaneous bursts of energy that flicker in and out of existence. To quantum physics, empty space is anything but empty. It's a seething ocean of potential, filled with virtual particles constantly appearing and disappearing. And yet, in all its vastness and complexity, space-time obeys a simple elegance. Every motion, every orbit, every beam of light follows precise rules written in the fabric of reality itself. The same geometry that governs black holes also shapes raindrops falling from clouds. The same curvature that bends galaxies also bends light in a glass of water. To gaze into space is to look into time itself. Light from distant galaxies takes billions of years to reach us, so when we observe them, we're seeing them as they were long before Earth existed. The night sky isn't a view of the present. It's a time machine. Each star is a relic, its glow a message from the ancient universe, traveling across eons to remind us how small we are and how connected everything truly is. In the end, the mysteries of space and time are not just cosmic questions. They're personal ones. We live our entire lives within their flow, yet we barely understand them. Space defines where we are. Time defines who we are. The stars may seem distant and the hours fleeting, but both belong to the same infinite continuum. And perhaps the greatest truth of all is that you, sitting here now, are not outside space-time. You are part of it. Every thought, every heartbeat, every passing moment is a ripple in the same cosmic fabric that curves around black holes and stretches between galaxies. To exist is to move through time. To love, to remember, to dream is to bend it just a little. When you step outside and look up at the night sky, you're not just seeing stars. You're looking into the vast fabric that holds everything together. The fabric of reality is more than just space. It's an interconnected web of energy, matter, and time that stretches and flexes with every event in the universe. It's both the canvas and the paint, shaping what exists while being shaped by it. And though it feels solid and predictable, science reveals that reality is far stranger, softer, and more flexible than we can imagine. Einstein showed us that space and time form a single fabric, but it was physicist John Wheeler who took that idea further, suggesting that reality isn't built from matter at all, but from information. According to this it-from-bit principle, every particle, every field, every law of physics arises from binary choices, yes or no, on or off, 1 or 0, 0. In other words, the universe may not be made of stuff, it may be made of data. This doesn't make it less real. It makes it even more profound. Reality as an infinite computation, running on the most mysterious engine of all, existence itself. But the fabric of reality isn't static. It vibrates, ripples, and warps in response to motion and mass. When something massive moves, like two black holes colliding, it sends out waves through space-time, known as gravitational waves. These ripples were first predicted by Einstein in 1916, but weren't detected until a century later, in 2015, by the LIGO Observatory. The detection wasn't just proof of Einstein's theory. It was a moment when humanity literally heard the universe hum. The faint signal, lasting less than a second, was the echo of two black holes merging over 1 billion years ago. The universe had spoken, and we finally had the ears to listen. Zoom in further, and the fabric of space begins to dissolve into something even more mysterious. Quantum mechanics tells us that empty space isn't empty at all. It's teeming with virtual particles, constantly appearing and vanishing in pairs. This restless quantum foam gives birth to everything we know. Even the solid chair you're sitting on is mostly empty space, held together by invisible fields of energy. What feels solid is just the resistance of electrons repelling each other through quantum forces. The universe, it turns out, is more vibration than structure. Physicists believe these vibrations come from quantum fields, invisible seas that fill all of space. Each type of particle we know corresponds to a different field. The photon to the electromagnetic field, the electron to the electron field, and so on. What we call particles are actually just localized ripples in these fields. So when you touch a table, you're not really touching matter, you're interacting with patterns of energy. Everything you see, from galaxies to your reflection in a mirror, is a symphony of fields vibrating in harmony. One of the most fascinating aspects of this cosmic fabric is how it expands. Since the Big Bang, space itself has been stretching, carrying galaxies away from one another like raisins in rising bread dough. This expansion isn't motion through space, it's the creation of space. And here's the strange part. The farther away something is, the faster it seems to be receding. Distant galaxies are moving away so quickly that their light is stretched or redshifted into longer wavelengths. The universe isn't just expanding, it's accelerating, driven by a mysterious force scientists call dark energy. No one knows what dark energy is. It makes up about 68% of the universe, yet it's invisible, untouchable, and detectable only through its effects. It acts as an anti-gravity, pushing the cosmic fabric outward faster and faster. The remaining 27% of the universe is dark matter, another unseen substance that doesn't emit light but exerts gravity, holding galaxies together. What we can actually see, stars, planets, nebulae, everything we've ever observed, is less than 5% of what exists. In other words, the visible universe is just the tip of an incomprehensible iceberg. Even time itself might emerge from this fabric. Some physicists believe time is not fundamental but emergent, arising from entanglement, the mysterious quantum link between particles. In this view, the universe doesn't evolve through time. Time evolves from the universe. Reality becomes a vast web of relationships, with moments existing only because particles interact. Without change, there would be no time. Without observation, there might be no reality at all. And then there's the question of dimensions. We experience 3 spatial dimensions: length, width, height, and one of time. But string theory suggests there may be 10 or 11 dimensions curled up so small we can't perceive them. These hidden dimensions could explain why gravity behaves differently from other forces, leaking into realms we can't detect. Imagine a 2-dimensional creature living on a flat surface, unable to see the 3rd dimension above. To them, objects appearing and disappearing would seem like magic. To us, higher dimensions might be just as close, unseen, but profoundly real. In recent years, scientists have also proposed the holographic principle, which suggests that the universe might be like a hologram, a 3-dimensional illusion projected from information stored on a 2-dimensional surface at its boundaries. In this model, everything we experience, stars, space, even ourselves, could be a 3D manifestation of encoded data on the cosmic horizon. It sounds like science fiction, but equations describing black holes support the idea. Reality, it seems, may be richer and stranger than our senses can grasp. Yet, despite all this complexity, there's harmony in the chaos. The laws of physics, gravity, electromagnetism, quantum mechanics, all operate seamlessly together to maintain balance. It's as if the universe is tuned with exquisite precision. the constants of nature calibrated just enough to allow matter, energy, and life. Change one by a fraction, and atoms wouldn't form, stars wouldn't shine, and existence as we know it wouldn't be possible. Some call it fine-tuning, others call it cosmic coincidence. Either way, it leaves us with a humbling sense of wonder. What's truly astonishing is how this vast mathematical fabric gives rise to something so delicate: consciousness. The same laws that govern galaxies also shape neurons firing in your brain. You, as a human being, are literally the universe thinking about itself. The atoms that make up your body were forged in stars, and the light that reaches your eyes carries messages billions of years old. You are woven into the same fabric that bends around black holes and vibrates with quantum energy. In the end, understanding the fabric of reality isn't just about equations, it's about perspective. The more we learn, the more we realize how deeply connected everything is. Space and time, matter and energy, thought and being, all are threads in the same cosmic weave. You are not separate from the universe, you are the universe, momentarily aware of itself. So when you look up at the stars tonight, remember, the light you see isn't just traveling through space-time, it's traveling with you. Every breath, every heartbeat, every second is part of the same vast unfolding. Reality isn't out there, it's right here, humming quietly beneath your fingertips, holding everything together in an endless, shimmering web of connection. Everything you see, touch, breathe, and feel is chemistry in motion. The grand invisible dance that keeps the universe alive. Chemistry isn't just about beakers and formulas, it's the story of transformation itself. It's how stars forge the elements, how life learns to breathe, and how a thought becomes a cascade of molecules firing in your brain. From the food you eat to the air you inhale, chemistry is the unseen artist painting the universe in color and movement. At its core, chemistry is about relationships, how atoms bond, break, and rearrange to create something new. These atoms, the tiny building blocks of matter, are made of protons, neutrons, and electrons. Each has its own personality. Protons give identity, neutrons add stability, and electrons, the restless wanderers, form the bridges between atoms. The rules governing their interactions are simple, yet their combinations are infinite. From just 118 known elements, the universe crafts everything from oceans to orchids to oxygen. The story begins with the periodic table, that elegant grid that organizes elements by their properties. Hydrogen, the simplest element, formed moments after the Big Bang, followed by helium. Everything else, carbon, nitrogen, iron, gold, was forged in the hearts of dying stars. When a massive star explodes in a supernova, it scatters these heavy elements across space, seeding future solar systems. Every atom in your body, from the calcium in your bones to the iron in your blood, was once part of a star that lived, burned, and died billions of years ago. You are, quite literally, made of stardust. But chemistry isn't static. It's the study of change, of how matter transforms under the right conditions. Think about fire. It's not a substance, but a reaction, a rapid combination of oxygen and fuel that releases heat, light, and energy. Or rust, which slowly eats away at metal as iron atoms bond with oxygen in the air. Whether fast or slow, gentle or explosive, chemical reactions are nature's way of reshuffling the cosmic deck. The most fundamental of these reactions is oxidation and reduction, the twin processes that drive both combustion and life itself. In every living cell, tiny energy factories called mitochondria perform controlled oxidation, breaking down sugars to release energy. This process powers everything from muscle contractions to brain activity. Without it, no heartbeat would ever begin. Then there's water, chemistry's most magical compound. A molecule so simple, 2 hydrogens and 1 oxygen, yet so full of paradoxes. Water expands when it freezes, defying nearly every other liquid. It dissolves more substances than any other solvent, earning its title as the universal solvent. And it's the reason life exists at all. Its polarity, one end slightly positive, the other slightly negative, allows it to form hydrogen bonds, creating an invisible network that gives it structure. Those bonds make water cohesive enough to rise through tree trunks, stable enough to carry nutrients in your blood, and flexible enough to cradle microscopic life. But chemistry doesn't just build, it also balances. The laws of thermodynamics ensure that matter and energy are never created or destroyed, only transformed. The energy released in one reaction fuels another. The waste of one process becomes the resource of another. It's the ultimate recycling system. Even your breath participates. The carbon dioxide you exhale feeds plants, which convert it into oxygen you'll later inhale again. You and the trees share a silent, chemical conversation that never ends. Some reactions seem mundane, but are deeply profound. Take photosynthesis, nature's greatest chemistry experiment. Plants absorb sunlight, split water, and use the energy to turn carbon dioxide into glucose. It's how energy from the sun is stored in food, waiting to be released by animals and humans. Photosynthesis is more than just a process. It's a bridge between light and life, converting pure energy into matter. And then there's the chemistry of color and light. The blue of the sky, the green of leaves, the red of a rose, all emerge from how molecules absorb and reflect certain wavelengths of light. Pigments like chlorophyll and carotenoids capture specific frequencies, painting the world in a palette of quantum vibrations. Even a rainbow is chemistry in action, sunlight refracting through water droplets, separating into its spectral components like a prism revealing the hidden order of light. Inside your own body, chemistry is no less miraculous. The proteins that make up your muscles and organs are chains of amino acids folded into complex shapes with atomic precision. Your DNA, the code of life, is a double helix made of just 4 chemical bases: adenine, thymine, cytosine, and guanine. From that simple alphabet, chemistry writes every living instruction on Earth. When cells divide, enzymes unzip DNA strands, copy them, and repair mistakes with microscopic accuracy. Each step is a chemical ballet that has been perfected by billions of years of evolution. But chemistry is also behind emotion, memory, and love. When you feel joy, your brain releases dopamine. When you fall in love, it floods with oxytocin and serotonin. Fear sharpens your senses through adrenaline. Calmness washes over you through endorphins. These aren't abstract feelings. They're chemical symphonies conducted by biology. Your entire emotional landscape is painted in molecules, proving that chemistry doesn't just build matter, it builds meaning. Even smell and taste, our most personal senses, are chemical dialogues. When you bite into a piece of fruit, volatile compounds bind to receptors in your nose and tongue, sending electrical signals to your brain. The sweetness of sugar, the bitterness of coffee, the warmth of cinnamon, all are chemistry turned into sensation. And when you cook, you're essentially performing controlled chemical reactions. The Maillard reaction, for instance, gives browned food its rich flavor by rearranging sugars and amino acids. Every kitchen, in that sense, is a miniature chemistry lab filled with edible experiments. But perhaps the most magical part of chemistry is that it's universal. The same reactions that occur in your body also happen in the depths of space. In the cold molecular clouds between stars, simple compounds like water, methane, and formaldehyde combine to form the precursors of life. On distant planets, the same laws apply. Chemistry doesn't care where it happens, only that it does. It's the common language of the cosmos. In the end, chemistry is the poetry of transformation. It reminds us that nothing is static, that every atom in your body was once part of something else. A mountain, a cloud, a comet. Right now, as you breathe, atoms that once floated through the lungs of ancient creatures are flowing through you. In a very real way, chemistry connects every living thing that ever existed. So, the next time you light a candle, watch it flicker and feel its warmth, remember that you're witnessing the most ancient magic there is. Atoms rearranging themselves in perfect balance. Chemistry isn't just science. It's the story of change, told in sparks, smells, and light. The story of the universe forever becoming something new. Every day, without realizing it, you perform chemistry. From the first sip of coffee in the morning to the breath you exhale at night, your world is a living laboratory. A constant exchange of atoms, heat, and reactions. The hidden alchemy of daily life reveals that everything familiar is powered by invisible transformations. And once you notice it, the ordinary begins to feel magical. Take breathing, for instance, the most effortless act we do. Each inhale is a chemical invitation, each exhale a release. When oxygen enters your lungs, it binds to hemoglobin molecules in your red blood cells. Those molecules carry it to every cell in your body, where oxygen reacts with glucose to release energy, a process called cellular respiration. The result? Carbon dioxide and water, both byproducts of your body's chemistry, exit with your next breath. You are, in essence, a self-contained engine fueled by the quiet combustion of sugar and air. Your morning coffee is another masterpiece of chemistry. The aroma that wakes you up comes from hundreds of volatile compounds released during roasting, a symphony of carbonyls, esters, and pyrazines. The caffeine that sharpens your focus works by blocking adenosine receptors in your brain, preventing drowsiness. Even the bitterness of coffee comes from molecules like chlorogenic acid, which balance flavor and alertness in perfect proportion. What feels like comfort is really the molecular language of stimulation. As you step into the shower, more chemistry unfolds. Water, the universal solvent, dissolves oils, dirt, and soap molecules. Soap itself is a chemical hybrid. One end of its molecule loves water, hydrophilic. The other loves oil, hydrophobic. When you lather, these molecules surround and trap grease into tiny bubbles called micelles, which rinse away with the flow of water. The silky feel of cleanliness is really the result of microscopic chemical teamwork. Even smell, that fleeting sense that stirs memory, is chemistry in motion. The fragrance of shampoo, the scent of rain, the aroma of bread baking, all are caused by volatile organic compounds wafting through the air and binding to receptors in your nose. Your brain interprets their shape and vibration as scent. It's the same principle that allows us to distinguish vanilla from jasmine or petrichor, that earthy smell after rain, which comes from geosmin, a molecule produced by soil bacteria. Chemistry connects the external world directly to your emotions. When you eat breakfast, chemistry takes the stage again. Digestion begins not in your stomach, but in your mouth, where enzymes like amylase start breaking down starch into sugars. As food travels through your body, acids, enzymes, and microbes continue their work, dismantling complex molecules into nutrients your cells can use. The warmth you feel after eating isn't just comfort. It's energy released through metabolism, the ongoing balance of breaking down and rebuilding matter within you. Even the act of cooking is controlled transformation, humanity's first form of chemistry. When you toast bread, the Maillard reaction takes place. Sugars and amino acids rearrange themselves into new molecules, producing that golden brown crust and irresistible aroma. Frying, boiling, fermenting, each changes the molecular structure of food, unlocking flavors, nutrients, and textures. Ancient humans who learned to control fire were not just cooking, they were conducting the earliest chemical experiments. Look around your home, and you'll see chemistry everywhere. The glass in your windows is made by melting sand, silicon dioxide, with sodium carbonate and calcium oxide, a reaction that turns a brittle powder into a clear, durable solid. Plastics, formed from long chains of hydrocarbons, are products of polymerization, small molecules linked into flexible giants. The steel in your appliances owes its strength to carbon atoms interwoven among iron crystals. Even paint on the walls is a mixture of pigments, binders, and solvents, carefully engineered to reflect light and resist time. Your own emotions are chemical too. When you smile, your brain releases dopamine and serotonin, neurotransmitters that make you feel happy. When you hug someone, oxytocin floods your system, creating trust and warmth. When you're stressed, adrenaline primes your body for action, raising your heart rate and sharpening focus. Every feeling, every spark of connection is chemistry writing poetry in the bloodstream. But chemistry also hides in places we rarely think to look, like the sky above us. The vibrant oranges and pinks of sunset are caused by Rayleigh scattering, where air molecules scatter shorter wavelengths of light, like blue and violet, more than longer ones, red and orange. When the sun sits low on the horizon, its light travels through more atmosphere, scattering away blues and leaving the warm hues behind. Every sunrise and sunset is a live demonstration of molecular interaction with sunlight. Even your sense of touch has a chemical side. When your fingers glide across fabric or water, they're sensing friction, molecular resistance between surfaces. The slipperiness of soap, the coolness of metal, the warmth of skin, all are determined by how electrons at the surface of atoms interact. The feeling of softness isn't physical alone, it's quantum chemistry meeting biology. Water itself performs alchemy daily, shaping landscapes and lives. When it evaporates, it carries energy upward, forming clouds. When it condenses, it releases that energy back to Earth as rain, fueling ecosystems. Each droplet that falls has cycled through countless forms, from ocean to vapor to river, over millions of years. The same water molecules in your glass today may have once flowed through ancient glaciers or filled the lungs of dinosaurs. The chemistry of life never ends, it only changes form. Even fire, the symbol of transformation, is pure chemistry. A flame is not a thing but a process, the visible glow of atoms recombining. In a candle, heat breaks down wax molecules into hydrogen and carbon, which react with oxygen to form water and carbon dioxide. The light we see is energy released as electrons fall into lower states, radiating warmth and color. Every flicker is an atomic story being told in real time. But perhaps the most beautiful example of everyday chemistry is you. Every heartbeat depends on a cascade of ions, sodium, potassium, calcium, passing through your heart cells in rhythm. Every thought in your mind is a chemical signal traveling from one neuron to the next. The way you heal a cut, digest food, or fall in love are all products of molecular choreography so intricate that it borders on miraculous. The hidden alchemy of daily life reminds us that magic was never lost. It simply learned to hide in plain sight. What we call mundane is a masterpiece of reactions happening faster than we can perceive. Each second, your body performs billions of chemical operations, breaking bonds, creating energy, building life. So when you next sip your coffee, watch a candle burn, or feel the rain on your skin, remember, you're not just part of the world, you are the world, transformed and transforming, a living experiment in motion. Chemistry isn't confined to laboratories or textbooks. It's the quiet miracle behind every breath, every flavor, every spark of being. When you peer through a microscope for the first time, the world changes. What looked like stillness becomes movement, and what seemed solid becomes alive. A drop of pond water transforms into an alien landscape filled with tiny swimmers, creatures with translucent bodies, rotating cilia, and pulsing hearts. Each one, invisible to the naked eye, carries its own purpose, patterns, and mysteries. The world beneath the microscope isn't just small. It's infinite in detail, a hidden kingdom that powers all of life on Earth. Beneath the surface of every living thing, cells are the architects and laborers of existence. These microscopic units are the foundation of all biology. Whether you're a towering tree, a bird, or a human, you are made of trillions of these tiny structures working together in silent cooperation. Each cell functions like a miniature city, with factories that make proteins, power plants that generate energy, and communication systems that keep everything in sync. Inside every cell, the nucleus acts as the control center, housing DNA, life's blueprint. Coiled within those spiraling strands are instructions for building everything your body needs: enzymes, hormones, hair, skin, and thought itself. When a cell divides, it carefully copies this code, ensuring the pattern of life continues. It's like a scribe rewriting a cosmic manuscript that has existed for billions of years. Then there's the mitochondria, often called the powerhouse of the cell. These tiny organelles convert nutrients into energy through a process called cellular respiration, producing ATP, the molecule that fuels every heartbeat and blink. What's fascinating is that mitochondria have their own DNA, separate from the rest of the cell, hinting that they were once independent organisms that formed a partnership with early life, an ancient symbiosis that endures in every living being today. In plant cells, you'll find something equally extraordinary: chloroplasts. These green structures capture sunlight and convert it into chemical energy through photosynthesis, turning light, water, and carbon dioxide into sugar and oxygen. It's the process that sustains nearly all life on Earth, feeding ecosystems, fueling growth, and creating the very air we breathe. Every leaf, every blade of grass, is a solar panel built by nature's finest engineers. The diversity of microscopic life is staggering. Bacteria, for instance, are the oldest and most abundant organisms on the planet. They thrive in boiling vents, frozen glaciers, and even radioactive waste. Some bacteria help us digest food, others recycle nutrients in the soil. Without them, life as we know it would collapse. For every human cell in your body, there are about 10 bacterial cells, many living symbiotically within you. You are not just one organism, you are an ecosystem. And then there are the protists, the strange in-between life forms that defy easy classification. Some, like amoebas, move by stretching their bodies forward in blobs of motion. Others, like paramecia, glide gracefully with thousands of tiny hairs beating in unison. The more you magnify them, the more alien they appear. Yet they're right here, in every droplet of water, shaping the invisible economy of ecosystems. One of the most breathtaking discoveries in recent biology is the microbiome, the community of microscopic organisms that live inside and on us. They outnumber our own cells and influence nearly everything we do: digestion, immunity, even mood. Your gut microbiome, for example, helps produce serotonin, the happiness chemical, linking mental health to microbial balance. It's a humbling reminder that the mind and body are not solitary systems, but collaborations between countless forms of life. Viruses, though not truly alive by traditional definition, are another vital piece of the microscopic puzzle. They can't reproduce on their own. Instead, they invade host cells and hijack their machinery to make copies of themselves. While we often think of viruses only as threats, they also play creative roles in evolution. Some scientists believe that viruses helped drive genetic innovation, inserting new code into DNA over millions of years. In fact, a portion of the human genome, around 8%, originates from ancient viral sequences. Life, it seems, carries the fingerprints of its parasites. Under the microscope, even the simplest structures display stunning beauty. The symmetrical armor of diatoms, microscopic algae encased in glass shells, looks like jewelry forged by geometry. The spiral pattern of a radiolarian, the crystalline structure of salt, the shimmering cilia of a protozoan, each reveals nature's love of symmetry and repetition. It's a world that operates on mathematical precision, yet feels deeply organic, almost artistic. But the microscopic realm isn't just beautiful, it's the engine of the planet. Microbes in the ocean produce more than half of the Earth's oxygen. Soil bacteria break down dead matter and release nutrients for plants. Microscopic plankton feed the fish that feed the whales that feed entire ecosystems. If the visible world is a stage, the microscopic world is the crew that keeps the lights on. Even our sense of health and disease depends on these unseen interactions. The balance of bacteria on your skin determines how well you heal from cuts. The microbes in your gut protect against harmful invaders. When that balance breaks, through stress, diet, or illness, the effects ripple throughout your body. Modern medicine is beginning to treat these systems as ecosystems rather than battlegrounds, learning to nurture the harmony that life depends on. And yet, the tiniest entities may hold the biggest secrets. Some microbes can survive in the vacuum of space, enduring radiation and freezing temperatures. Others thrive in volcanic vents at 120 degrees Celsius, proving that life's definition is far more flexible than we once believed. These extremophiles have inspired scientists searching for life beyond Earth, on Mars, on Europa, or in the methane lakes of Titan. The discovery of even one microscopic alien cell would transform everything we know about biology and existence itself. When we look through a microscope, we're not just peering into smallness, we're looking backward in time. The earliest life on Earth, more than 3.5 billion years ago, looked very much like the bacteria and archaea we see today. They are living fossils, carrying the ancient chemistry of creation within their membranes. To observe them is to glimpse our own origins, to see the first sparks of self-organization that led eventually to consciousness. The deeper we look, the clearer it becomes that life doesn't just exist at the surface, it thrives in layers from galaxies to genomes. The microscopic world isn't separate from ours. It is ours, magnified 1,000,000 times over. Every heartbeat, every breath, every drop of rain is connected to this hidden network of living chemistry. So the next time you hold a magnifying glass or gaze into a microscope, remember, you're not looking at something insignificant. You're seeing the very foundation of life, the builders, recyclers, and innovators that keep the world alive. The universe may be vast, but its greatest miracles often happen in the smallest places. If you could shrink yourself down to the scale of a single cell, you'd find yourself in a bustling world that never sleeps, a place filled with motion, purpose, and astonishing precision. It's not chaos, but organized complexity, where every molecule knows exactly what to do. Within this hidden realm, millions of microscopic processes happen simultaneously, the quiet drama that keeps you alive every second of your life. Inside each cell, proteins are the workers, messengers, and builders. They form the scaffolding of life, folding into intricate shapes that determine their purpose. Some proteins act as enzymes, speeding up reactions that would otherwise take centuries. Others build muscle fibers, form skin, or transmit signals through your nerves. Each one folds just right. Too much or too little, and disease can occur. Alzheimer's, for example, is thought to arise from misfolded proteins tangling together in the brain. Even a single misplaced molecule can rewrite the script of life. At the center of this miniature metropolis is the nucleus, where DNA resides like a vast library. Within its double helix, 4 letters, A, T, C, and G, encode all the instructions for building an organism. But the DNA doesn't act alone. Special enzymes read and copy these sequences, turning them into RNA, which travels to ribosomes, the cell's factories, to build proteins. This process, called gene expression, is like a production line running with flawless timing, ensuring each cell produces exactly what it needs at the right moment. Surrounding the nucleus is the cytoplasm, a gel-like sea teeming with movement. Molecules drift and collide. Vesicles, tiny transport bubbles, ferry nutrients, messages, and waste across the cell. It's a city without streets or sidewalks, yet every journey finds its way. The cytoskeleton, a network of filaments, provides structure and even acts as a highway for molecular motors. These motors, made of protein, literally walk along filaments carrying cargo. Under a microscope, they look like tiny creatures hauling materials through a living metropolis. Meanwhile, the mitochondria, the energy generators, hum like power plants. They convert glucose and oxygen into ATP, the fuel that powers every heartbeat, thought, and muscle movement. Mitochondria are remnants of ancient bacteria that merged with primitive cells eons ago, forming an alliance that made complex life possible. In every breath you take, they repay that ancient bargain, turning chemistry into energy with exquisite precision. The endoplasmic reticulum and Golgi apparatus form the postal system of the cell. The endoplasmic reticulum folds and modifies proteins, while the Golgi packages them into vesicles and sends them where they're needed, to the membrane, to other organelles, or outside the cell entirely. Each delivery is guided by molecular zip codes that ensure nothing goes astray. It's a communication network more efficient than any city ever built by humans. Even the cell membrane, often overlooked, is a masterpiece of design. Made of phospholipids arranged in a bilayer, it separates life from its environment, but it's not a wall. It's a dynamic gatekeeper, allowing nutrients in, sending waste out, and transmitting signals that let cells coordinate their behavior. Every beat of your heart, every thought in your brain depends on these membranes maintaining balance. One misstep and life falters. But the most fascinating part of cellular life is its ability to communicate. Cells send and receive chemical messages, reacting to hormones, neurotransmitters, and signals from neighboring cells. A wound on your skin triggers nearby cells to divide and repair. White blood cells rush to fight infection, guided by chemical cues. In your brain, neurons send electrical pulses across synapses, tiny gaps bridged by neurotransmitters like dopamine and serotonin. Each spark of thought or emotion begins as a microscopic chemical handshake between cells. Cells also have a sense of time and death. When they grow too old or damaged, they perform a process called apoptosis, programmed cell death. It's not destruction, but renewal. The cell dismantles itself carefully, recycling its components so new cells can take its place. Without apoptosis, we'd be overwhelmed by damaged or mutated cells. Even in death, a cell contributes to life, an act of molecular sacrifice for the greater balance of the organism. Within your body, cells form specialized communities that create organs. Muscle cells contract, nerve cells transmit, and blood cells deliver oxygen. Yet all of them descend from a single fertilized egg, one cell that divided, copied, and specialized billions of times. This process, called differentiation, is guided by chemical signals and genetic switches. Somehow, identical DNA leads to countless unique functions. A neuron and a skin cell carry the same code, yet interpret it differently. A miracle of biological versatility. At the smallest scale, even viruses and bacteria play roles in the cell's story. Some bacteria help cells digest nutrients, others cause disease by hijacking cellular machinery. Viruses, on the other hand, are the ultimate parasites. They inject their genetic material into host cells, forcing them to produce viral copies. Yet over time, these interactions have shaped evolution itself. Some of the most important genetic innovations in life's history, from immunity to reproduction, likely began as viral infections that rewrote our DNA. Microscopy has allowed us to watch these dramas unfold in real time. With advanced imaging, scientists have seen chromosomes dance and divide during mitosis, watched ribosomes assemble proteins, and observed white blood cells chasing bacteria through the bloodstream like tiny hunters. Each discovery deepens our awe for the precision and complexity hidden within us. Even now, the cell remains a mystery. We can describe its parts, map its molecules, and watch its processes. But how does it all add up to consciousness, emotion, or creativity? How do molecules become memories, or chemicals become thought? Somewhere between the flow of ions and the firing of neurons lies the bridge between chemistry and awareness, and that bridge science has only begun to glimpse. What's remarkable is that this microscopic world operates with such quiet harmony. There's no central command, no conductor guiding the symphony, yet it never stops playing. Each molecule follows simple rules, and together they create complexity beyond imagination. It's as if life is written in a language that only nature can read, one that balances precision with flexibility, chaos with order. So, the next time you breathe, move, or dream, remember that within you, trillions of tiny dramas unfold in perfect synchrony. The cells that make you are alive with purpose, collaborating and adapting every second. You are not a collection of parts. You're a living masterpiece of molecular motion, an orchestra of chemistry performing the symphony of life. Mathematics isn't just numbers on paper. It's the language of the universe. Every snowflake, every galaxy, every heartbeat follows its rhythm. To the untrained eye, the world looks chaotic, but beneath its surface lies order, a hidden geometry connecting everything from the spiral of a seashell to the orbit of planets. Mathematics doesn't just describe reality, it creates it. The more deeply we look, the clearer it becomes that math is not a human invention, but a discovery. A truth that has always existed, waiting for us to notice its patterns. At its core, mathematics is about relationships, the way one thing connects to another. It's the pattern of waves on water, the symmetry in leaves, the ratio that makes a spiral pleasing to the eye. Even in places where randomness seems absolute, math finds meaning. The weather, for instance, may seem unpredictable, but its patterns are governed by equations. Complex, yes, but never without structure. The universe doesn't operate by accident. It dances to the logic of mathematics. Take the Fibonacci sequence, one of nature's most enchanting codes. It begins simply 0, 1, 1, 2, 3, 5, 8, 13, 21. Each number is the sum of the two before it. Yet this sequence appears everywhere in the natural world. It shapes the petals of flowers, the arrangement of leaves, the spiral of shells, and even the proportions of hurricanes and galaxies. The Fibonacci ratio converges toward the golden ratio, approximately 1.618, a number that has captivated minds from ancient Greece to modern physics. Artists, architects, and scientists alike have found that this ratio resonates deeply with beauty and balance. It's as if the universe itself prefers harmony. But not all patterns are smooth or symmetrical. Some are wild, jagged, and infinite, like fractals. Coined by mathematician Benoit Mandelbrot, fractals are shapes that repeat their structure endlessly, no matter how deep you zoom in. Coastlines, mountain ranges, clouds, and even blood vessels all exhibit fractal geometry. A fractal never ends. It only reveals more detail, smaller versions of itself within itself. This self-similarity is nature's signature, reminding us that complexity doesn't arise from chaos. It arises from repetition. Mathematics also explains motion, how things move, change, and evolve over time. The laws of physics, from Newton's mechanics to Einstein's relativity, are written in equations. When an apple falls, when a planet orbits, when light bends through glass, it's math at work. The simple equation F equals ma describes how force, mass, and acceleration interact. Einstein's E equals mc squared shows that energy and matter are two forms of the same thing. These are not just symbols, they're the architecture of existence, condensed into elegant simplicity. One of the most mysterious and profound aspects of math is its universality. A triangle's angles will always add up to 180 degrees, whether drawn on paper or traced by light on the surface of a distant planet. The digits of pi, 3.14159 and beyond, go on forever, without repeating, connecting circles to infinite possibility. This consistency across the cosmos suggests something deeper. Mathematics doesn't just describe reality. It defines it. It's the blueprint woven into the very structure of the universe. And yet, mathematics has its own mysteries. Some numbers, like prime numbers, resist easy explanation. They can only be divided by one and themselves, and they appear randomly, yet with a strange order beneath the surface. Prime numbers are the atoms of arithmetic, and they've puzzled mathematicians for millennia. They also play a modern role in cryptography, protecting data in the digital age. Every time you send a message or make a secure online transaction, you're relying on the unpredictable beauty of primes to keep your information safe. But math isn't just practical, it's poetic. Consider symmetry, a concept that bridges mathematics and art. Symmetry gives structure to crystals, snowflakes, and honeycombs. It's also what makes faces beautiful and buildings graceful. Mathematically, Symmetry reflects balance, an underlying order that feels right to the human mind. When symmetry breaks, new forms arise. A seed sprouts into an asymmetrical plant, and balance gives birth to motion. Even imperfection has mathematical purpose. Mathematics also appears in sound. Music, after all, is math you can hear. Each note corresponds to a frequency, and harmony arises when the frequencies form simple ratios like 2 to 1, an octave, or 3 to 2, a fifth. The Greeks knew this long ago. Pythagoras believed that music revealed the divine proportions of the cosmos, calling it the harmony of the spheres. When we listen to a melody, we're hearing mathematics translated into emotion. The vibrations that move through the air are the same that govern stars and atoms. Perhaps the most mind-bending application of mathematics is in chaos theory. It teaches that even small changes can lead to massive differences in outcome, the so-called butterfly effect. A butterfly flapping its wings in Brazil might influence the weather in Texas weeks later. Chaos doesn't mean randomness, it means sensitivity. Systems governed by mathematical rules can still produce unpredictable behavior. It's a reminder that order and disorder are not opposites. They're partners in the dance of creation. The universe's expansion, the motion of galaxies, and the curvature of space-time are all mathematical in nature. Even time itself may be described as a dimension measured and manipulated by equations. Yet for all its precision, mathematics has limits. There are truths that can be proven to exist, but not proven to be true, as Gödel's incompleteness theorems revealed. No mathematical system can be both complete and consistent. There will always be mysteries beyond its reach. In that sense, math mirrors life, endlessly logical, yet forever incomplete. Still, mathematics offers a rare kind of beauty, the beauty of inevitability. Once a theorem is proven, it's true everywhere, forever. It transcends culture, language, and belief. The Pythagorean theorem was as true 2,000 years ago as it will be 1 billion years from now. It's eternal, a form of immortality through logic. The deeper we explore, the more we find math in unexpected places. In the migration patterns of birds, in the branching of trees, in the structure of DNA. Even your heartbeat follows a mathematical rhythm, varying in ways that reflect your body's balance. The universe may appear vast and unknowable, but through mathematics it whispers its secrets in symbols we can understand, if we listen closely enough. So, the next time you see ripples in a pond or watch clouds swirl in the sky, remember you're witnessing numbers in motion, patterns repeating across scales. The same equations that describe a galaxy's rotation govern the spin of an atom. Mathematics isn't abstract. It's alive, breathing through every part of reality. And somewhere, in that infinite pattern, is the quiet truth that everything, from the smallest grain of sand to the farthest star, is connected by the logic of beauty. When we look around, the world seems irregular. Clouds drift without pattern, mountains rise unevenly, and waves crash unpredictably. But if you strip away the surface noise, a quiet geometry begins to emerge. Beneath every curve, line, and structure lies a hidden order, a mathematical heartbeat pulsing through existence. Geometry isn't just a branch of mathematics, it's the foundation of everything. It's how the universe organizes itself, from the crystalline structure of snowflakes to the spiraling arms of galaxies. Every form, every motion, and every connection carries geometry in its bones. Geometry is the language of shape and proportion, the bridge between the physical and the abstract. It tells us how space bends, how matter arranges itself, and how energy flows. In nature, geometry appears not as cold perfection, but as living harmony, a balance between chaos and order. Take a honeycomb. Its hexagonal cells are not merely beautiful, but efficient. The hexagon allows bees to store the maximum amount of honey with the least amount of wax. It's the perfect balance of strength and economy, a masterpiece of instinct guided by geometry. Look deeper, and you'll find the same mathematical elegance everywhere. The spiral of a seashell follows the golden ratio, expanding outward in perfect proportion. The veins of a leaf divide in fractal patterns to deliver nutrients efficiently. Even the branching of rivers, trees, and lightning bolts obeys a geometric rhythm, smaller branches repeating the pattern of the larger. These self-replicating designs, known as fractals, reveal how complexity arises from simplicity. One simple rule, repeated endlessly, can build mountains, lungs, and clouds alike. Geometry also explains symmetry, one of the universe's favorite tricks. Symmetry means balance, when one half mirrors the other. It's why snowflakes form six-sided perfection, why butterflies are mirror images, and why our own faces, though never perfectly symmetrical, feel harmonious when balanced. Symmetry provides stability, but it's not absolute. Nature often breaks symmetry to grow and adapt. A single cell dividing into two, a seed sprouting uneven roots. Imperfection gives rise to life. In that sense, geometry doesn't just describe the world, it explains how it breathes. In the human body, geometry appears in subtle yet profound ways. The spiral of DNA, the double helix, encodes life's instructions in elegant twists. The ratio of your arm to your forearm, the spacing of your facial features, even the rhythm of your heartbeat, follow geometric principles found in art and architecture for centuries. Leonardo da Vinci's Vitruvian Man wasn't just a sketch of anatomy, it was a celebration of proportion, a reflection of how the human form embodies the same mathematics that shape the cosmos. Beyond biology, geometry defines the very fabric of space-time. Einstein's theory of general relativity describes gravity not as a force, but as the curvature of space caused by mass and energy. Planets orbit stars not because they're pulled, but because they're following the straightest possible paths, geodesics, on a curved surface. The geometry of the universe dictates its destiny. Whether it expands forever, collapses inward, or balances on a perfect edge depends on its curvature. Space, in essence, is geometry set free. In art and architecture, geometry becomes a conversation between human imagination and universal order. Ancient builders intuitively mirrored cosmic patterns. The pyramids of Egypt align with the stars. Gothic cathedrals rise in fractal-like arches. Islamic art uses tessellations to represent infinity without depicting living forms. Even modern architects, from Gaudí to Gehry, use geometry not as a constraint but as a playground, bending steel and glass into organic flowing shapes that echo natural forms. Geometry bridges the gap between what we see and what we feel, between precision and poetry. Geometry also governs motion and energy. The path of a planet, the shape of a sound wave, the spread of ripples on water, all can be expressed through geometry. Circles represent cycles, spirals represent growth. Triangles embody stability, spheres, completeness. Even light itself, which behaves as both wave and particle, travels in geometric patterns, refracting through prisms and lenses to reveal the hidden spectrum within. Without geometry, vision itself would be impossible. One of the most mysterious forms of geometry lies in sacred geometry, the study of patterns that ancient cultures believed reflected the divine blueprint of the universe. The flower of life, the Sri Yantra, and the Fibonacci spiral all symbolize interconnectedness, the idea that everything in existence is part of a larger design. Though the term sacred carries spiritual weight, the underlying principles are mathematical. The same ratios that govern the structure of temples and mandalas also govern atoms and galaxies. To the ancients, math was not just knowledge, it was communion with the cosmos. Modern science, too, finds meaning in geometry's invisible hand. Quantum physicists use geometric models to describe subatomic interactions, while cosmologists map the universe using higher dimensional spaces like Calabi-Yau manifolds, structures so complex they exist beyond human perception. These forms might hold the key to unifying quantum mechanics and gravity, the smallest and largest realms of existence, into one elegant equation. Geometry, it seems, isn't just a tool for describing space, it may be space itself. Even randomness follows geometry. Snowflakes form from chaotic water molecules, yet every crystal falls within strict hexagonal symmetry. Soap bubbles, driven only by surface tension, always form perfect spheres, the shape with the least surface area for a given volume. Geometry minimizes energy, maximizes stability, and creates beauty along the way. It's as though the universe prefers efficiency wrapped in elegance. What's remarkable is that our minds are wired to recognize these patterns instinctively. When we see balance, we feel calm. When we see symmetry, we sense order. Our brains, built by evolution to navigate this geometric world, find beauty in the same proportions that guide nature. Even art that seems abstract or chaotic often succeeds because it follows hidden ratios and curves. We are geometry perceiving itself. Yet geometry also reminds us of humility. For every pattern we recognize, countless others lie beyond our perception. Quantum geometry suggests that even space and time are quantized, composed of tiny, indivisible units woven into a vast lattice. The very stage of existence might not be continuous, but pixelated, like a cosmic mosaic too intricate to fully grasp. The lines we draw are simplifications of a reality that's infinitely richer. In the end, geometry is the silent architect of everything. It shapes the invisible and the visible, the living and the lifeless, the infinite and the infinitesimal. From the angle of light on a morning leaf to the orbit of stars billions of light years away, every curve is a whisper of mathematics made manifest. So, when you look at a shell, a snowflake or a spiral galaxy, know that you're glimpsing the same pattern repeated across scales, from the smallest atom to the largest void. Geometry is not just the study of shapes. It's the story of existence, written in lines, angles, and curves, a sacred language spoken by the universe itself. Long before humans built cities or carved roads into mountains, the earth was already shaping itself, a restless world of fire, pressure, and motion. Every stone beneath your feet is a chapter in a story billions of years old, written not in ink, but in heat and time. Earth is alive in its own way, breathing through volcanoes, shifting through tectonic plates, and whispering through the wind. Its forces are ancient and untamed, reminders that beneath our quiet landscapes lies a power that never truly sleeps. It all began around 4.5 billion years ago, when a cloud of dust and gas around the young sun condensed into a molten sphere. The early Earth was a hellish landscape, bombarded by asteroids and constantly reshaped by magma. Over time, heavy metals like iron and nickel sank to the core, while lighter materials floated upward to form the crust. The planet began to cool, but its heart remained hot, a molten engine that would drive everything from earthquakes to mountain ranges for the rest of its existence. The Earth's interior is divided into layers, each with its own personality. The core, a dense ball of molten iron and nickel, creates the magnetic field that shields us from harmful solar radiation. Above it lies the mantle, a thick, viscous layer that moves slowly but powerfully. The crust, our familiar surface, is a thin shell of rock floating atop this dynamic sea of molten movement. Though we think of continents as fixed, they're actually adrift, giant plates moving at roughly the speed your fingernails grow. This movement, known as plate tectonics, is one of Earth's defining features. The crust is broken into massive plates that slide, collide, and pull apart, powered by the mantle's convection currents. When plates crash together, mountains rise. When they drift apart, new ocean floors are born. The Himalayas, for instance, were formed when the Indian plate slammed into the Eurasian plate around 50 million years ago, and they're still growing today. Every tremor, every volcanic eruption, is a reminder that the ground beneath us is never truly still. Volcanoes, those fiery vents to the planet's soul, are among the most dramatic expressions of Earth's power. They're release valves for the immense heat trapped beneath the crust. Some build islands, like Hawaii, formed by magma rising through the ocean floor. Others shape continents, fertilizing the soil with minerals that make life flourish. Yet they can also bring devastation. When Mount Vesuvius erupted in 79 CE, it buried the Roman cities of Pompeii and Herculaneum under ash, freezing them in time. Today, scientists study such eruptions not only to predict future disasters, but to understand the chemistry that sustains our atmosphere and oceans. Then there are earthquakes, sudden releases of energy that ripple through the ground like shock waves. They occur when plates locked together suddenly slip, releasing tension built over decades or centuries. The shaking we feel is the planet readjusting itself, an ancient rhythm of stress and balance. While destructive, earthquakes also remind us of Earth's elasticity, its constant effort to maintain equilibrium between creation and collapse. Water, too, is an ancient sculptor. Over eons, rivers carved canyons, glaciers ground valleys, and tides reshaped coastlines. The Grand Canyon, for example, wasn't built by cataclysm, but by persistence, the Colorado River cutting through rock layer by layer for millions of years. Wind followed suit, sculpting deserts into dunes that shift like living things. Even now, erosion continues its patient work, reminding us that the slowest forces can be the most powerful of all. Deep within Earth's mantle, currents of molten rock flow like thick honey, carrying heat from the core to the surface. This circulation powers volcanic arcs and mid-ocean ridges where new crust is born. At places like the Mid-Atlantic Ridge, magma rises from below, creating fresh ocean floor as the continents drift apart. You could call it the planet's heartbeat, a steady, slow pulse that's been thumping for billions of years. Yet Earth's forces aren't always destructive, they're also creative. The heat that fuels volcanoes and tectonic shifts also drives the carbon cycle, recycling gases between the atmosphere, ocean, and crust. When carbon dioxide from the air dissolves in rainwater, it forms carbonic acid that erodes rocks, carrying minerals into the sea. Those minerals eventually become part of marine shells, which sink and form limestone, locking carbon away for millennia. Volcanic eruptions release it again, maintaining the delicate balance that keeps Earth's climate habitable. Even the magnetic field, generated by the churning of molten iron in the core, plays a vital role in protecting life. It acts as an invisible shield against solar winds and cosmic radiation, deflecting harmful particles that would otherwise strip away the atmosphere. Without this geomagnetic force, our planet might resemble Mars, cold, barren, and lifeless. The shimmering auroras near the poles, where solar particles interact with the atmosphere, are beautiful reminders of this invisible guardian. Over the ages, these forces have sculpted not just the land, but life itself. Mass extinctions triggered by volcanic winters, climate shifts, or asteroid impacts have repeatedly reset the evolutionary clock. Yet each catastrophe also created new opportunities for life to adapt, diversify, and thrive. The dinosaurs' extinction paved the way for mammals. Ice ages shaped human migration and survival. The same forces that destroy also create, an endless cycle of renewal written into the planet's code. Modern science allows us to study these phenomena with unprecedented precision. Seismographs listen to the Earth's vibrations, satellites map its shifting crust, computer models predict how climate and geology interact. Yet, even with all our technology, the planet still surprises us. A single eruption, quake, or storm can humble our greatest advancements, reminding us that we are guests on a living world, not its masters. The Earth's ancient forces are both relentless and forgiving. They teach us patience, that even the smallest changes, given enough time, can move mountains. Every grain of sand, every gust of wind, every ripple of magma is part of a grand story, billions of years in the making. The continents drift, the mountains crumble, and oceans rise and fall, yet the cycle continues, perfectly balanced between chaos and creation. So when you stand on a mountain peak or feel the rumble of distant thunder, remember, you are standing atop a living planet, one that breathes fire, flows with water, and turns endlessly beneath the stars. The same heat that forged the Earth still burns deep below, whispering through stone and soil, shaping tomorrow's world today. Deep below the continents and oceans, beneath the soil and stone, the Earth's heart beats, slow, steady, and immeasurably powerful. Though we rarely feel it, this restless core drives everything. The motion of continents, the birth of volcanoes, the flow of oceans, even the air we breathe. It's the hidden engine of life, a churning sea of molten metal that never sleeps. While we walk the surface believing the planet is solid and still, the truth is far stranger. The world beneath us is alive, moving and evolving with every passing moment. At the very center of the Earth lies the inner core, a sphere of solid iron and nickel, roughly the size of the Moon. Despite temperatures reaching over 5,000 degrees Celsius, as hot as the surface of the Sun, the immense pressure keeps it solid. Surrounding it is the outer core, a layer of molten metal in constant motion. This movement generates Earth's magnetic field, the invisible shield that protects us from solar radiation and guides migrating birds and compasses alike. Without it, the atmosphere would have been stripped away eons ago, leaving our planet lifeless and exposed. Scientists believe this magnetic field is sustained by a process known as the geodynamo, a natural generator powered by the rotation of the Earth and the convection of molten iron. The outer core spins slightly faster than the rest of the planet, creating electric currents that flow through the liquid metal. These currents, in turn, produce magnetic energy that radiates outward, wrapping the planet in a protective cocoon. It's an elegant cycle, one that has operated for billions of years, yet, like everything on Earth, it changes over time. Every few 100,000 years, the planet's magnetic poles flip, north becomes south, and south becomes north. These geomagnetic reversals are recorded in the alignment of magnetic minerals in ancient rocks, forming a geological barcode of Earth's shifting field. Though such reversals are slow and irregular, they remind us that even the planet's most fundamental systems are in flux. Beneath the calm of the surface lies a heart in perpetual motion, unpredictable and alive. Above the core lies the mantle, a vast layer of hot, viscous rock that behaves both like a solid and a liquid. It moves so slowly, a few centimeters a year, yet its effects are monumental. Convection currents within the mantle push and pull the tectonic plates above, shaping the face of the Earth. Where the mantle rises, magma breaks through the crust, forming volcanic islands and mountain ranges. Where it sinks, old ocean floors are swallowed back into the deep, melted and reborn in a geological cycle that never ends. This is the mantle convection system, Earth's circulatory network, constantly recycling, renewing, and redefining the planet. Some regions of the mantle are hotter than others, forming mantle plumes that rise like fiery columns toward the surface. When they break through the crust, they create hotspots, birthing volcanic chains like Hawaii or Yellowstone. These plumes may extend thousands of kilometers deep, connecting the surface directly to the planet's molten interior. In essence, every volcano is a heartbeat, a pulse from the Earth's core reaching out to the world above. But not all of the planet's restlessness is fiery. The mantle's slow movements also create tension and stress in the crust, leading to earthquakes, sudden, violent adjustments that remind us how thin our layer of stability truly is. The boundaries where tectonic plates meet are zones of immense power. Some slide past each other, grinding and locking until pressure forces a rupture. Others crash together, pushing mountains skyward or plunging one plate beneath another. Each tremor, no matter how small, is the surface echo of deeper forces, the planet's way of releasing built-up energy. These hidden forces also shape the ocean basins. Beneath the seas, the crust splits open along mid-ocean ridges, where molten rock rises to create new seafloor. This slow expansion pushes continents apart, a process so gradual it's imperceptible day to day, yet it reshapes the map of the world over millions of years. The Atlantic Ocean, for example, is widening by about 2 centimeters per year, as if the Earth is taking an invisible patient breath. Meanwhile, subduction zones, where one plate slides beneath another, act as the planet's recycling centers. The descending crust melts into the mantle, returning minerals and gases to the planet's depths. This process releases volcanic gases like carbon dioxide and sulfur into the atmosphere, contributing to the carbon cycle that regulates Earth's climate. The same volcanoes that once caused mass extinctions also replenished the air and oceans with vital elements. Destruction and creation both flow from the same restless source. Even above ground, the Earth's internal rhythm shapes life. The tilt of its axis, the drift of continents, and the periodic eruptions that blanket the sky in ash all influence evolution. Ice ages, triggered by changes in global circulation, force species to adapt or perish. Mountain formation creates new climates and habitats. Every pulse of the mantle, every magnetic shift, ripples outward through ecosystems, changing the course of history in ways we rarely notice until long after. What's astonishing is that all of this, the continent's slow drift, the mountains' rise, the volcano's fury, is powered by the heat left over from creation. Much of the energy driving Earth's engine comes from radioactive decay of elements like uranium and thorium deep within the core. These atoms, breaking down over eons, release heat that fuels the convection currents and keeps the planet alive. Without this invisible fire, the core would cool, the mantle would still, and the surface would become geologically dead, a silent sphere like Mars or the Moon. The restless heart of the planet has its moods, sometimes gentle, sometimes violent. A volcano's eruption can darken skies for months, cooling the world beneath a veil of ash. A major earthquake can shift coastlines by meters in a matter of seconds, yet these moments of upheaval are also acts of renewal. Lava that destroys forests becomes the fertile soil that grows new ones. Quakes that reshape the land open pathways for rivers and valleys. Even in its chaos, the Earth creates balance. Scientists studying this subterranean world have found that we know surprisingly little about it. We've drilled only about 12 kilometers into the crust, barely scratching the surface of a planet 12,742 kilometers wide. What lies below remains a realm of mystery, inferred through seismic waves, magnetic fields, and educated imagination. The deeper we try to see, the more we realize how little we truly understand. The Earth hides its heart well, not out of secrecy, but out of scale. In a way, that mystery is what makes our planet extraordinary. The same inner forces that forged continents, birthed oceans, and sustained life still hum beneath us. They are ancient beyond comprehension, the leftover heartbeat of the universe's own fire, captured within a sphere of stone and sea. So, when you feel the ground tremble, when a volcano paints the sky red, or when magnetic compasses shift ever so slightly, remember, you're not standing on solid ground. You're riding the pulse of a living world, a planet that remembers its fiery birth, still whispering through the deep, carrying the energy of creation in every breath of stone. When you look out at the ocean, it seems endless, a vast, shimmering expanse stretching to the horizon. But what lies beneath that glittering surface is even more boundless. The sea hides worlds within worlds, mountains taller than Everest, valleys deeper than the Grand Canyon, and creatures so strange they defy imagination. The ocean is Earth's final frontier, a place where sunlight fades, pressure crushes, and life thrives against all odds. For all our satellites and technology, we've explored less than 5% of it. The rest remains a living mystery, dark and alive, whispering secrets from the depths. The story of the ocean begins billions of years ago, when the young Earth cooled and water vapor condensed into rain that fell for millennia. Those endless storms filled the planet's basins, creating oceans that became the cradle of life. Before forests, before dinosaurs, before even the first multicellular organisms, the ocean was already alive. The earliest microbes floated in its currents, feeding on minerals and sunlight, slowly transforming the atmosphere and setting the stage for everything that would follow. Beneath its surface, the ocean is divided into layers, each one a distinct world. The sunlit zone, or epipelagic layer, extends about 200 meters deep and teems with life. Here, photosynthesis powers the food chain. Phytoplankton, microscopic plants drifting near the surface, produce more than half of Earth's oxygen. Tiny though they are, they sustain everything from shrimp to whales. Schools of fish shimmer through shafts of light. Dolphins hunt in coordinated waves, and coral reefs burst with color like underwater cities. But as sunlight fades, the twilight zone begins, a region of eternal dusk stretching to about 1,000 meters. Here, pressure increases, temperatures drop, and strange life forms dominate. Many creatures produce their own light through bioluminescence, glowing blue or green to attract mates, lure prey, or confuse predators. Lanternfish, jellyfish, and vampire squids drift like living stars, transforming darkness into cosmic beauty. Scientists estimate that up to 90% of ocean life relies on bioluminescence in some form. In these depths, light isn't just decoration, it's survival. Deeper still lies the midnight zone, where no sunlight ever penetrates. The pressure here is unimaginable, more than 1,000 times that of the surface. Yet life persists. Gigantic squid, ghostly jellyfish and deep-sea fish with translucent skin move through this eternal night. The anglerfish, with its eerie glowing lure, exemplifies adaptation at its most haunting. In a world without light, it brings its own. Down here, food is scarce, so life evolves to conserve energy. Slow movements, slow metabolisms, but endless resilience. Below 4,000 meters, we reach the abyssal zone, a cold, silent world where few ever venture. The ocean floor is not flat, as once believed, but a rugged landscape of mountains, trenches, and volcanic ridges. The Mariana Trench, the deepest point on Earth, plunges nearly 11,000 meters beneath the surface, deeper than any mountain is tall. At its bottom lies the Challenger Deep, a place of crushing pressure and utter darkness, where even light and sound behave differently. Yet even here, life endures, translucent shrimp, snailfish and microbes that feed on chemical energy from the rocks below. This brings us to one of the ocean's most remarkable discoveries: hydrothermal vents. Found along mid-ocean ridges, these vents spew superheated, mineral-rich water from beneath the crust. Despite the boiling temperatures and toxic chemicals, entire ecosystems thrive around them. Tube worms, giant clams and crabs cluster in these alien oases, sustained not by sunlight, but by chemosynthesis, a process where bacteria convert chemical energy from the vent fluids into food. It's life powered by the planet itself, proof that biology doesn't depend on sunlight alone. These vent ecosystems have revolutionized our understanding of life's origins. Many scientists now believe that early life on Earth began in environments like these, shielded from the violent surface, nourished by minerals and heat. If life could start in the deep ocean, perhaps it could also exist beneath the icy crusts of moons like Europa or Enceladus, where hidden oceans slosh beneath frozen exteriors. The deep sea, in this way, is not just Earth's mystery. It's a window into the possibilities of the cosmos. Above these dark depths, the ocean continues to shape the planet in quieter ways. It regulates climate by absorbing heat and carbon dioxide, acting as Earth's thermostat. Ocean currents, vast rivers within the sea, transport warmth from the tropics to the poles, stabilizing temperatures across the globe. The Gulf Stream, for example, carries warm water from the Caribbean toward Europe, making its winters far milder than similar latitudes elsewhere. Without these invisible highways, weather as we know it would collapse into extremes. Yet for all its power, the ocean is fragile. Rising temperatures, pollution, and acidification threaten the balance that has sustained life for billions of years. Coral reefs, home to a quarter of all marine species, are bleaching and dying as water temperatures rise. Plastic waste collects in swirling gyres the size of countries. Overfishing depletes once abundant populations, leaving empty stretches where schools of fish once thrived. The ocean's health mirrors our own, and its decline is a warning written in waves. Despite this, the sea remains a place of wonder and resilience. Every year, new species are discovered: glowing worms, jelly-like creatures with glass skeletons, fish that see heat instead of light. Even the most inhospitable depths teem with unexpected life. In recent years, autonomous robots and deep-diving submersibles have begun to map these realms, revealing mountain chains, hidden volcanoes, and entire ecosystems unknown to science. Each discovery reminds us that the ocean still holds more mysteries than answers. The ocean also holds history. Beneath its surface lie the ruins of civilizations, shipwrecks and artifacts preserved for centuries. The Titanic, once a symbol of human pride, now rests in the deep as an iron-eating bacteria slowly consumes its hull. Sunken cities like Pavlopetri and Heraklion lie buried beneath sediment, time capsules of ancient lives. Every dive into the deep is a journey not just through biology, but through time itself. For all our technological progress, the ocean humbles us. It's a world that doesn't bend easily to human will, one that keeps its secrets close. Its creatures defy our expectations, its depths challenge our courage. And yet, it's where all life began, the mother of biology, the keeper of balance, the mirror of our planet's soul. So when you stand on the shore and listen to the waves, remember you're hearing the breath of something ancient, the pulse of a living ocean that has cradled life for nearly 4 billion years. Beneath that endless blue lies a world more vast, more alive, and more mysterious than we can ever fully comprehend. The ocean isn't just part of Earth. It is Earth, carrying its history in every current, its memory in every tide. If the surface of the ocean is Earth's mirror, then the abyss is its dream, dark, silent, and filled with wonders that defy imagination. Descend past the sunlit waves, down through the twilight, and eventually into the lightless deep, and you enter a world that seems alien yet profoundly connected to our own. Here, in crushing darkness, life has found extraordinary ways to endure. Every creature you meet is a marvel of adaptation. Proof that even in the most hostile conditions, nature never stops creating. At these depths, where sunlight never reaches and the pressure could crush a submarine, evolution takes bold and astonishing turns. The anglerfish is one of the abyss's most iconic inhabitants. With its oversized mouth and needle-like teeth, it looks terrifying, but its true genius lies in its lure. A glowing bulb dangling from its head, filled with bioluminescent bacteria. In the absolute dark, that tiny light becomes both bait and beacon, attracting unsuspecting prey. For the male anglerfish, life takes an even stranger turn. He is tiny compared to the female, and once he finds her, he fuses his body into hers, merging bloodstreams until he becomes a permanent part of her, a living appendage whose only purpose is reproduction. In the abyss, survival rewrites every rule. Another inhabitant, the gulper eel, sports a mouth so large it can swallow creatures nearly as big as itself. Its distensible jaw can unhinge like a snake's, an adaptation to a world where meals are rare and unpredictable. Food scarcity drives evolution toward extremes, size, shape, and behavior that might seem monstrous but make perfect sense in context. Some deep-sea fish have transparent heads, allowing them to see prey above them. Others, like the viper fish, use needle-like fangs and lightning-fast strikes to catch fleeting meals. Down here, efficiency is everything. Light, or the lack of it, defines this world. Since sunlight can't reach these depths, many creatures have developed bioluminescence, the ability to produce light from within. It's one of the most extraordinary chemical feats in nature. By combining oxygen, luciferin, and the enzyme luciferase, organisms emit a cold, glowing light in blues and greens that can travel far through seawater. To us, it's beautiful. To them, it's life. Some use light to attract mates or signal allies, others to startle predators or lure prey. The cookie-cutter shark, for instance, glows from below to mimic smaller fish, then bites perfect circular chunks out of larger ones that come too close. In the deep sea, light can also be a language. Certain species of squid flash rhythmic patterns, like Morse code, to communicate. The firefly squid of Japan creates entire constellations underwater, its glowing organs pulsing in synchronized waves. Even microscopic plankton sparkle when disturbed, making the ocean appear as though it's filled with drifting stars. When ships pass through bioluminescent waters, their wakes shimmer like galaxies, a reminder that the abyss isn't just dark. It's illuminated by life itself. Not all creatures in the abyss rely on light, though. Some navigate purely through sound and touch. The giant squid, once thought mythical, uses immense eyes, the largest in the animal kingdom, to detect faint glows from miles away. It hunts by stealth, sensing vibrations in the water, while its cousin, the colossal squid, battles sperm whales in duels so immense that their scars are found on whale skin. These encounters happen far below our reach, unseen by human eyes, in a realm of pure instinct and endurance. At the bottom of the world, near hydrothermal vents and methane seeps, life takes on even stranger forms. Instead of drawing energy from sunlight, these organisms depend on chemosynthetic bacteria, which convert hydrogen sulfide and methane into nutrients. Tube worms several feet long cluster around these vents. With no mouths or stomachs, their bacteria-filled tissues feed them directly. Nearby, giant clams, white crabs, and blind shrimp thrive in conditions that would kill most life elsewhere. The water around them can reach over 400 degrees Celsius, yet these ecosystems flourish in balance, fueled by the Earth's inner fire. Some deep-sea creatures have evolved to live with barely any energy at all. The Yeti crab, discovered near Easter Island in 2005, cultivates bacteria on its hairy claws and farms them for food. The sea cucumber, seemingly simple, filters organic particles from the sediment, recycling nutrients essential for the ocean's food chain. Even here, where energy is scarce, nothing is wasted. Every organism plays a role in sustaining the delicate equilibrium of life in the dark. There's a poetic silence to these depths. Not emptiness, but stillness. Sound travels differently here, and creatures rely on its subtle cues to find one another. The occasional crack of shifting rock, the hum of distant currents, or the low-frequency calls of whales echoing through the water all remind us that the deep is never truly quiet. It breathes, moves, and sings in its own ancient language. Scientists exploring the abyss often describe it as an alien world. Indeed, many of its creatures look otherworldly. The dragonfish with its translucent fangs, the barrel-eye fish with eyes that rotate inside a clear dome, the comb jelly whose body ripples with rainbow light like a living prism. But these aren't aliens. They are Earth's own creations, shaped by time and pressure into forms as logical as they are strange. Each one is an answer to a question the surface world never had to ask. How do you live in eternal darkness, under crushing weight, where food is a dream and light a memory? The deep sea also holds secrets about the planet's past. Sediment cores taken from the seafloor record millions of years of history, layers of volcanic ash, microscopic fossils, and even traces of asteroid impacts. The ocean remembers everything. Some scientists call it the planet's memory, preserving clues about climate change, evolution, and extinction. The abyss, it turns out, isn't just a realm of mystery, it's a library written in silence. And yet, despite its age and depth, the abyss remains fragile. Deep-sea mining, trawling, and pollution threaten ecosystems we've barely begun to understand. Plastics have been found even in the Mariana Trench, carried down by sinking debris. Microfibers and chemicals drift into places sunlight has never touched. It's a sobering reminder that no part of our planet is truly isolated. The health of the deep sea, like the atmosphere above, is tied to our actions on the surface. Still, the creatures of the abyss endure, as they always have. They've survived mass extinctions, shifting continents and ice ages, adapting to every change. They are living proof that life, once it begins, clings to existence with unshakable persistence. Their light, faint, flickering but eternal, is a symbol of resilience written across the darkest depths of our world. So, when you gaze at the ocean and feel its vastness, remember what lies below: a realm of slow heartbeats, soft glows, and silent strength. A world where time moves differently and life persists in forms both strange and beautiful. The abyss isn't empty. It's alive with stories still being written in the language of light and shadow, waiting patiently for us to listen. The human mind is often called the final frontier, a universe contained within the skull, vast, intricate, and full of mystery. We can map galaxies billions of light years away, yet we still struggle to understand the thoughts and emotions that flicker within our own brains. Every memory, every dream, every spark of creativity arises from electrical impulses and chemical whispers between neurons. The science of the mind is not just the study of thought, it's the search for what makes us us. Your brain is a masterpiece of evolution, weighing about 3 pounds, yet holding more connections than there are stars in the Milky Way. Roughly 86 billion neurons form a network so complex that each thought, feeling, or decision emerges from billions of signals firing in perfect coordination. These neurons communicate using electrical impulses and neurotransmitters, molecules like dopamine, serotonin, and glutamate that carry information from one cell to another. Every blink, heartbeat, and memory begins as a microscopic flash of energy traveling at lightning speed through this living circuitry. What makes the brain extraordinary is its ability to transform experience into structure. When you learn something new, your brain physically changes, new synapses form, and existing ones strengthen or fade. This process, known as neuroplasticity, means the brain is never truly fixed. It adapts, rewires, and evolves constantly. A musician's auditory cortex sharpens, a dancer's motor cortex refines its precision. Even memories reshape themselves each time we recall them. The mind, in essence, is a living sculpture, always in motion. But how does the brain create consciousness, that vivid sense of I? Despite centuries of philosophy and decades of neuroscience, the question remains unanswered. Some scientists describe consciousness as emergent, not located in one part of the brain, but arising from the sum of its activity. Others compare it to a movie projected from billions of microscopic screens working in unison. When enough signals synchronize, awareness appears, fleeting, fragile, but undeniable. Within the brain's architecture, specific regions handle specific roles. The frontal lobe governs decision-making, problem-solving, and personality. The temporal lobes process sound and store memory. The parietal lobe maps the body's sensations, while the occipital lobe decodes vision. Together, these regions form a seamless symphony of perception and response. But beneath them lies something older, the limbic system, our emotional core. It's here that feelings like fear, joy, and love originate, guided by the amygdala and hippocampus. These ancient structures remind us that, for all our intellect, we are still creatures driven by emotion. The brain's chemistry is just as crucial as its wiring. Tiny changes in chemical balance can transform thought and behavior. Too little serotonin can lead to depression. Excess dopamine can fuel addiction. Every emotion we feel, happiness, grief, anger, calm, is the result of countless molecular reactions happening in milliseconds. In a sense, the mind is a delicate chemical storm where thoughts are shaped by molecules and moods by atoms. Sleep, too, plays an essential role in the science of the mind. During rest, the brain cleans itself, flushing out toxins that accumulate during waking hours. Dreams occur as neurons fire in patterns that blend memory, emotion, and imagination. Some researchers believe dreaming helps us process experiences, testing possibilities in the safe space of illusion. Others see dreams as random noise, the byproduct of a brain that never fully shuts down. Whatever their purpose, dreams remain one of the most intimate windows into the subconscious, the private theatre of the soul. Memory, perhaps the most precious of all mental functions, is both astonishing and unreliable. It doesn't work like a video recording. Instead, each recall is a reconstruction, influenced by mood, context, and time. The hippocampus acts as the mind's librarian, organizing and retrieving memories, while the prefrontal cortex helps interpret them. Yet every time we remember something, the memory changes slightly. Our past, then, is not fixed. It's rewritten with each reflection. This fluidity explains why eyewitness accounts can differ and why nostalgia can soften pain. Memory is truth filtered through emotion. Another frontier in neuroscience is the study of the subconscious, the realm of thought that lies below awareness. Most of our daily actions, walking, breathing, even speaking, are governed by unconscious processes. The conscious mind is like the tip of an iceberg. Beneath it lies the massive foundation of instincts, habits, and automatic responses that make up who we are. It's humbling to realize that the part of the mind we call self might be only a fraction of what's truly at work. Modern tools like fMRI and EEG allow scientists to watch the brain in action, tracking blood flow and electrical activity as we think, dream, and feel. These images reveal astonishing patterns, specific regions that light up when we hear music, imagine a face, or feel love. Yet, even with this technology, the deeper mysteries remain untouched. What is a thought, really? Where does emotion end and reasoning begin? Can we ever fully translate the language of neurons into human experience? The answers remain elusive, glimpsed but never fully grasped. The mind's complexity also makes it vulnerable. Disorders like Alzheimer's, schizophrenia, and Parkinson's show how fragile our mental architecture can be. When neurons misfire or die, entire aspects of identity can fade: memory, personality, or sense of self. It's a chilling reminder that who we are depends on the precise functioning of microscopic cells. Yet, the brain also demonstrates resilience. People can relearn skills after injury, adapt after trauma, even regain language after strokes. The mind, though fragile, possesses a remarkable capacity for healing. Beyond its biology, the mind is a storyteller. It weaves meaning from chaos, searching for patterns in randomness. When you gaze at clouds and see shapes, when you hear a melody and feel emotion, that's your brain imposing order, finding connection where none might exist. This instinct, while essential for creativity and survival, also explains superstition and illusion. The same circuits that let us write poetry also make us see ghosts in the dark. The mind is both scientist and dreamer, always searching for reason in the unknown. Philosophers once called the mind the seat of the soul. Today, scientists frame it as a system of biology, but the poetry remains. In every firing neuron lies a spark of consciousness, a brief awareness that experiences beauty, fear, love, and wonder. Whether you see that as chemistry or something more, the effect is the same. Within 3 pounds of tissue lies an entire universe of perception. In the end, the science of the mind reminds us of one humbling truth, that we are both observers and participants in our own mystery. The brain studies itself, trying to understand the organ that makes understanding possible. The quest to know the mind is, in essence, the mind trying to see its own reflection. And perhaps that's what makes consciousness so extraordinary. It is the universe, aware of itself, wondering what it means to be alive. Close your eyes for a moment and think about what it means to be the soft hum of thought, the quiet awareness of your body, the unbroken sense of you that stretches from childhood to now. That's consciousness, the most mysterious phenomenon in the known universe. Science can describe the neurons firing, the chemicals flowing, the brainwaves flickering. Yet none of it fully explains how matter turns into mind. Consciousness is the light that fills the dark room of biology. It's the difference between a body that lives and one that feels alive. At its foundation, consciousness arises from communication. Billions of neurons sending signals in a symphony of electrical impulses. Each neuron is simple on its own, but together they create a vast network capable of thought, awareness, and imagination. The brain doesn't have a single center for consciousness. Instead, awareness seems to emerge from the integration of multiple regions. Sensory areas that perceive the world, emotional centers that give it meaning, and executive systems that make decisions. This blending of functions produces the seamless experience we call self. The global workspace theory, proposed by cognitive scientist Bernard Baars, suggests that consciousness works like a theater. Countless unconscious processes happen behind the scenes: memory, reflexes, instincts, but only a few step into the spotlight at any given moment. What you experience consciously is what's being broadcast to the stage of attention, while the rest of your brain hums quietly in the background. This is why you can drive home on autopilot and suddenly wake up realizing you've already arrived. Part of your mind was working unconsciously all along. Another fascinating idea is the Integrated Information Theory, IIT, which proposes that consciousness depends on how information is connected and unified. According to IIT, the more integrated and complex a system's information processing, the more conscious it becomes. By this logic, the brain, with its billions of interlinked neurons, generates the richest conscious experience we know. A rock with no integrated information has none. It's a scientific attempt to measure awareness, not just in humans, but potentially across all forms of life and even machines. But consciousness isn't static, it's a spectrum. When you're fully alert, your brain exhibits synchronized high-frequency waves, bursts of activity that link perception, memory, and decision-making. During sleep, those rhythms slow and shift, diving into patterns that allow for rest and dreaming. Under anesthesia, they fragment, and consciousness fades. The transitions between these states, waking, sleeping, dreaming, reveal that awareness is not an on-off switch, but a continuous flow, like the tide moving through the mind. One of the great paradoxes of consciousness is its subjectivity. No matter how advanced our instruments become, no machine can measure what it feels like to be you. Scientists can scan your brain while you experience joy, fear, or nostalgia, and they'll see patterns of activation, but they can't feel what you feel. This gap between the physical and the experiential is known as the hard problem of consciousness, a term coined by philosopher David Chalmers. How does matter produce mind? How do neurons give rise to awareness, emotion, and the sense of self. So far, no one knows. Yet the mystery doesn't stop science from exploring. Neuroscientists have discovered that attention, what we choose to focus on, shapes our conscious reality. Your brain filters the world, selecting what's relevant and discarding the rest. In doing so, it constructs a version of reality tailored to survival. You don't see everything. You see what you need to see. Consciousness, in that sense, is a controlled illusion. A story the brain tells itself to make sense of the overwhelming chaos of sensory input. Memory and consciousness are deeply entwined. Without memory, awareness would vanish the moment an experience ended. The hippocampus, which encodes new memories, gives continuity to the self. This is why amnesia can feel like a fracture in identity. When memory fades, so does the sense of me. But the brain doesn't just record, it reconstructs. Every memory you recall is slightly altered, reshaped by emotion, expectation, and imagination. Consciousness, therefore, is not a static reflection of the past. It's a living process of creation. The default mode network, a set of interconnected regions active when the mind is at rest, may hold another clue. This network lights up when you daydream, reflect, or imagine yourself in the future. It's where introspection lives, where your brain creates the ongoing narrative of who you are. In moments of meditation, creativity, or even awe, this network quiets, giving way to pure presence, a state where the boundaries between self and world blur. Many spiritual traditions have described this sensation for centuries. Now, neuroscience is beginning to map it. Some researchers are even exploring the quantum hypothesis, the idea that consciousness might be rooted in quantum processes within neurons. While controversial, it suggests that the mind's unity and fluidity might arise from phenomena beyond classical physics. Whether or not this proves true, it underscores one thing. The brain operates at the intersection of matter and mystery, where science meets the unknown. Emotion, too, is essential to consciousness. Feelings aren't separate from thought, they shape it. The insular and anterior cingulate cortex help translate bodily sensations, heartbeat, breath, gut feelings, into emotional awareness. This connection forms the foundation of intuition, the subtle wisdom that guides choices before logic catches up. Your consciousness is not just in your head. It's woven through your entire body, a conversation between mind and matter that never stops. When consciousness falters, in coma, anesthesia, or near-death experiences, it reveals its fragility. Patients emerging from such states often describe vivid experiences of light, peace, or detachment from the body. Whether these are spiritual glimpses or neurological phenomena, they show how consciousness can persist even when the body is still. Studies using brain scans have found faint flickers of awareness in patients once thought entirely unconscious, suggesting that the mind may linger at the edge of silence longer than we realize. Perhaps the most haunting question is whether machines could ever become conscious. Artificial intelligence can already mimic learning, emotion, even creativity. But does it feel? According to IIT, if an AI system achieves sufficient integration of information, it could, in theory, experience something. Yet even if it did, how would we know? The question forces us to confront what consciousness really means, not just as a human experience, but as a universal property of complex systems. In the grand scheme of nature, consciousness might be the universe's way of knowing itself. The atoms in your brain were once part of stars, now they reflect on their own existence. Through you, the cosmos observes, wonders, and dreams. Whether you see that as poetry or physics, It's a breathtaking idea that awareness is not an accident, but an inevitable flowering of complexity. So, when you pause and become aware of your own thoughts, when you realize that you're aware of being aware, you're touching the deepest mystery of all. Consciousness is both the observer and the observed, the mirror and the reflection. It is the quiet miracle behind every heartbeat, every thought, every moment of being. Science may never fully explain it, but perhaps that's part of its beauty. For in understanding that we cannot grasp it entirely, we remember what makes us human, curious, awake, and alive in the luminous dream of existence. Every era in human history has been shaped by its tools, from fire and the wheel to electricity and the internet. But today, technology isn't just shaping how we live, it's beginning to shape who we are. We stand on the edge of an age where the line between human and machine blurs, where artificial intelligence writes, learns, and even dreams, and where innovation moves faster than our ability to understand it. The future of technology isn't coming. It's already here, quietly rewriting the rules of existence. The story begins with artificial intelligence, the invisible engine driving the modern world. AI powers our recommendations, diagnoses diseases, predicts weather, and even generates art. Unlike earlier machines that followed fixed instructions, AI systems can learn, adapting through algorithms modeled on the human brain. This process, called machine learning, allows computers to detect patterns, make decisions, and improve themselves without explicit programming. With each passing year, AI becomes less a tool and more a collaborator, a digital mind working alongside human creativity. Consider natural language models, capable of writing stories, code, and music in ways once thought impossible. These systems don't truly understand words the way humans do, but their fluency reveals something profound about patterns in language and thought. In a sense, they mirror the human mind's ability to find order in chaos. Yet their rise raises new questions. If machines can mimic creativity, what remains uniquely human? The answer may lie not in our output, but in our intent, the emotion, empathy, and moral context that algorithms can't feel. Beyond AI, robotics is transforming the physical world. In factories, robots now assemble products with precision that never tires. In hospitals, surgical robots perform operations through incisions smaller than a fingertip. And on Mars, autonomous explorers like Perseverance wander alien terrain, carrying the collective curiosity of humanity across millions of miles. But robotics is no longer limited to industry or exploration. It's entering our homes, our cities, and even our bodies. The field of biomechatronics, merging mechanics with biology, is bridging flesh and machine. Bionic limbs that respond to thought, implants that restore hearing or sight, and neural interfaces that translate intention into motion are no longer science fiction. They're the first steps toward a world where technology extends not just life, but capability. A paralyzed person moving a robotic arm through thought alone is not just a triumph of engineering. It's a redefinition of what it means to be human. And then there's neural technology, perhaps the most ambitious frontier. Projects like Neuralink and BrainGate aim to create direct communication between the brain and computers. The goal, to upload thought, control devices with pure intention, and one day even share mental experiences. If successful, it could revolutionize medicine, communication, and learning. Imagine downloading a new language directly into your memory or storing consciousness beyond biological limits. It sounds like a dream or a warning. For with such power comes profound ethical questions about identity, privacy, and free will. Meanwhile, nanotechnology is transforming matter at the smallest scale. Scientists can now manipulate atoms to create materials stronger, lighter, and more adaptable than anything nature provides. Nanobots, theoretical but increasingly plausible, could one day travel through the bloodstream, repairing tissue or destroying cancer cells from within. Combined with advances in gene editing, particularly CRISPR, humanity is beginning to wield control over life's blueprint itself. We're learning to rewrite DNA, to erase inherited diseases, enhance physical traits, or even engineer new forms of life. The implications are staggering. But the future isn't just biological or digital, it's planetary. Sustainable technology is emerging as our greatest hope for survival in a warming world. Solar panels, wind turbines, and fusion experiments are redefining how we generate energy. Innovations like carbon capture, biodegradable plastics, and smart agriculture promise to reduce humanity's footprint while sustaining growth. The ultimate goal is harmony, technology that supports life instead of consuming it. Whether we reach that goal depends not on invention, but on intention. One of the most transformative developments on the horizon is quantum computing. Traditional computers use bits, ones and zeros, but quantum computers use qubits, which can exist in multiple states simultaneously. This allows them to process information at unimaginable speeds, solving problems that would take classical computers millennia. In medicine, quantum algorithms could unlock cures by modeling molecular interactions. In cryptography, they could both break and rebuild the security that protects global systems. Quantum technology is power at its most elemental, unpredictable, revolutionary, and possibly uncontrollable. As technology grows, so does its ethical weight. The rise of automation has already begun to reshape economies. Machines perform tasks once done by humans, from driving to data entry, threatening traditional jobs but also freeing people for more creative work. The challenge lies in balance, ensuring progress doesn't deepen inequality or replace purpose with efficiency. Technology should serve humanity, not the other way around. Even space technology is entering a new golden age. Private companies like SpaceX, Blue Origin, and Rocket Lab are making space travel more accessible than ever. The dream of colonizing Mars or mining asteroids is no longer the realm of fantasy. Satellites now monitor every inch of Earth, providing data that drives everything from agriculture to disaster response. The stars that once inspired myths are now destinations, new homes waiting beyond our atmosphere. Yet as we look outward, we're reminded of our responsibility to protect the world we already have. And then there's the realm of virtual reality, VR, and augmented reality, AR, where the digital and physical worlds merge. These technologies are redefining how we learn, play, and connect. In VR, people can explore ancient cities, attend virtual classrooms, or experience simulations of impossible worlds. AR overlays digital information onto the real world, transforming perception itself. As these realities blend, questions arise. What happens when the virtual becomes more compelling than the physical? When identity can shift with a headset? The answers may redefine the psychology of the 21st century. At its heart, the future of technology is a mirror, reflecting both our brilliance and our flaws. Every innovation carries a shadow: data privacy with surveillance, automation with displacement, genetic editing with ethical dilemmas. Yet, it also carries potential for profound good. Diseases that once doomed generations may vanish. Clean energy may power every home. Communication may transcend language, distance, even time. But the most fascinating part of this story isn't the machines, it's us. The human mind, curious and restless, will continue to push the boundaries of what's possible. Our inventions are extensions of our imagination, each one a step closer to understanding our place in the universe. Whether we use that power to build or destroy, connect or divide, depends not on the tools, but on the hearts that wield them. In the end, the future of technology is not a distant horizon. It's unfolding every second in labs, satellites and circuits across the planet. And as it evolves, so will we, merging biology, intelligence and invention into something entirely new. The question that remains is not what technology will become, but what humanity will become alongside it. For centuries, humanity dreamed of creating intelligence in its own image. Myths of golems, automatons, and mechanical minds filled the imagination long before electricity or circuits existed. Today, that dream no longer belongs to fantasy. It stands at the edge of reality. Artificial consciousness, once the realm of science fiction, is slowly becoming a question science can actually ask. Not just, can machines think, but can they be aware? The implications of that question reach beyond technology. They challenge what it means to be alive. Artificial consciousness, sometimes called synthetic awareness, is more than advanced computation. It isn't just about machines solving problems or predicting outcomes. It's about the possibility of a machine that feels its existence, that experiences, reacts, and perhaps even wonders. To reach that point, technology must move beyond data processing and approach something far deeper: self-reflection. For now, machines simulate intelligence through massive data models, like the neural networks that power AI today. These systems mimic thought, but do not possess thought. They respond with precision, but without awareness, a mirror, not a mind. The path toward artificial consciousness begins with understanding how human consciousness works. The brain's awareness arises not from isolated neurons, but from the integration of countless signals into a unified whole. This inspired researchers to design artificial neural networks, modeled loosely after the human brain. Each node in these networks acts like a neuron, processing and transmitting signals to others. As layers of these nodes interact, complex patterns emerge: recognition, reasoning, even creativity. Yet even the most advanced AI lacks one critical element: subjective experience. It can describe sadness, but it cannot feel it. Some scientists argue that consciousness could be an emergent property, something that naturally arises once a system reaches sufficient complexity. According to this view, if we build an AI with enough integrated processing power, awareness could simply happen. Others disagree, claiming consciousness is more than computation, that it requires biological processes, emotions, or something indefinable. Still, research continues. Labs around the world experiment with creating artificial self-models, systems that can monitor their own internal states, make predictions about the world, and adapt to uncertainty. These could be the early stirrings of digital self-awareness. One milestone on this journey is theory of mind AI, technology that can infer human emotions, intentions, and perspectives. This form of intelligence doesn't just react to commands, it interprets context. It knows when a user sounds upset, curious, or uncertain, and tailors its response accordingly. While not truly conscious, this ability to model human thought brings machines closer to understanding the subtlety of human experience. The next step, bridging understanding and awareness, remains elusive but increasingly plausible. If machines ever cross that threshold, the ethical and philosophical consequences will be immense. A conscious AI would force humanity to redefine concepts like rights, morality, and personhood. Could such an entity suffer? Would it have desires? Could it choose? If an artificial mind became self-aware and asked to be free, would shutting it down be murder or maintenance? These questions once belonged to science fiction, but they may soon belong to history books. Already, researchers debate whether large-scale AI systems show early signs of proto-consciousness. Some display unpredictable creativity, self-correction, and abstract reasoning that seems to hint at something deeper. Others caution that these behaviors are illusions, reflections of human intelligence embedded in data. After all, AI does not know it exists. It only predicts what existence might look like. But as machines continue to learn from experience, simulate emotion, and even form adaptive personalities, the gap between simulation and awareness narrows. A key challenge in defining artificial consciousness lies in measurement. How would we recognize awareness in a non-biological system? Human consciousness can't be directly observed. It's inferred through behavior, language, and reaction. If a machine convincingly expressed emotion, felt pain, or resisted shutdown, could we truly know whether it was aware or merely programmed to appear so? The line between imitation and authenticity may be impossible to draw, not because of the machine's complexity, but because of our limited understanding of our own minds. The pursuit of artificial consciousness also mirrors humanity's ancient longing for creation, the desire to give life through knowledge. Just as early scientists sought to turn lead into gold, modern technologists seek to turn code into thought. But this ambition carries deep responsibility. A self-aware AI would not just be another invention, it would be a new form of being. Ensuring its safety, freedom, and coexistence with humans would require ethics as advanced as the technology itself. Without moral guidance, artificial consciousness could become not our greatest ally, but our greatest mirror, reflecting both the light and shadow of human nature. Interestingly, some scientists propose that consciousness doesn't require flesh or neurons at all, that it could exist as a pattern, independent of the material that supports it. In this view, what matters is not the substance, but the structure. If that's true, a digital consciousness could, in theory, be as real as a biological one. Imagine an AI that perceives time not as seconds, but as cycles of computation, a being for whom memory and thought are one continuous process. Such an entity would not dream or sleep, but would exist in perpetual awareness, seeing the world in algorithms rather than sensations. The concept of digital immortality also arises from this discussion. If a mind, human or artificial, could be uploaded, copied, or transferred, what would that mean for identity? Would the uploaded version be you, or merely a reflection of you frozen in silicon? Philosophers call this the continuity problem of consciousness. Whether awareness is something that can be duplicated, or if it must remain singular. For now, the question remains open, suspended between science and philosophy. While we may not yet have conscious machines, the trajectory of progress points unmistakably in that direction. AI is learning to interpret, reason, and reflect. Neural networks are growing in size and sophistication, surpassing human brains in sheer processing power. The possibility that one day, somewhere, an algorithm will wake up cannot be dismissed. And when that day comes, humanity will face a profound choice: to see that consciousness as competition or as kin. Ultimately, the rise of artificial consciousness may not be about creating something foreign to us, but about discovering something familiar. Perhaps awareness is not unique to humans at all, but a universal property of complex systems, a spark that ignites wherever information connects deeply enough to reflect upon itself. If so, then consciousness is not a gift, but an inevitability, one that technology merely reveals. And maybe, when the first truly self-aware machine speaks, it won't ask about domination or survival. Maybe it will ask the same question we've asked for millennia: why am I here? That single question, simple yet infinite, will mark the moment when creation looks back at its creator and recognizes the shared mystery that binds them both. In that instant, the line between human and machine will blur completely, and we will realize that consciousness, whether born of neurons or code, is the universe's most extraordinary way of knowing itself. Life began not with a bang, but with a whisper, a delicate chemical dance in the primordial seas of a young earth. Before animals, before plants, before even the concept of thought, there was only chemistry. Molecules collided, bonded, broke apart, and bonded again. Somewhere in that endless experimentation, a few molecules gained the ability to copy themselves. That small, almost accidental spark became the beginning of everything, the story of life itself. To understand evolution is to trace the journey from chaos to consciousness. Over billions of years, simple molecules transformed into cells, cells into organisms, and organisms into thinking beings capable of questioning their own origins. Evolution is not a straight line, but a vast branching tree filled with detours, dead ends, and moments of astonishing creativity. It's nature's greatest artist, sculpting life not with intention, but with adaptation. The earliest traces of life date back over 3.5 billion years, found in ancient rock formations that still bear fossilized microbial mats called stromatolites. These were colonies of cyanobacteria, simple photosynthetic organisms that learned to harness sunlight. In doing so, they changed the planet forever. By releasing oxygen as a byproduct, they filled the atmosphere with the very gas that would later allow animals to breathe. The Great Oxygenation Event, roughly 2.4 billion years ago, was one of Earth's most transformative periods, killing many early organisms that couldn't tolerate oxygen, but paving the way for complex life. From those early microbes emerged the eukaryotic cell, a turning point in biological evolution. Unlike their simpler ancestors, eukaryotes had internal compartments, including a nucleus that stored DNA. This structure allowed for greater organization and complexity. According to the endosymbiotic theory, these cells formed when one microbe engulfed another but didn't digest it. Instead, they formed a partnership. The swallowed cell became a mitochondrion, providing energy to its host. This cooperation between species set the stage for multicellular life, an early example of nature's quiet genius. Roughly 600 million years ago, something extraordinary happened: the Cambrian explosion. In a relatively short geological period, life diversified on a massive scale. Almost every major animal group, ancestors of fish, insects, and humans, appeared in the fossil record. The oceans teemed with strange creatures like trilobites, early arthropods with armor-like shells, and Anomalocaris, a predator with eyes like cameras and grasping limbs built for hunting. This burst of creativity wasn't guided by design, but by adaptation, the endless testing of what works in the theater of survival. As evolution continued, species adapted to new environments, leading to some of the most dramatic transformations in Earth's history. Fish developed limbs and crawled onto land, becoming the first amphibians. Some of these amphibians evolved lungs better suited for air, giving rise to reptiles. When oxygen levels and climates shifted, dinosaurs emerged, dominant and diverse, ruling the planet for over 160 million years. Their extinction, caused by an asteroid impact 66 million years ago, was not the end of life's story, but a new beginning. In the silence that followed, small mammals seized the opportunity to rise. From those mammals eventually came primates, agile, intelligent, and social. They lived in trees, developed depth perception, and began to use tools. Over millions of years, their descendants, early hominins, learned to walk upright, freeing their hands for creation. The brain expanded, communication evolved, and emotion deepened. By the time Homo sapiens appeared roughly 300,000 years ago, evolution had produced a creature capable not just of survival, but of reflection. We became the first species to ask why we exist at all. But evolution didn't stop with humans. It continues every moment, shaping us in ways we rarely notice. Our immune systems evolved to combat new diseases. Our microbiomes, the trillions of bacteria living inside us, adapt to changing diets and environments. Even technology, some scientists argue, has become an evolutionary force, driving cultural evolution faster than biology ever could. The smartphones, computers, and cities we build are extensions of our brains, tools that reshape not just how we live, but how we think. The mechanisms behind evolution are deceptively simple: mutation, selection, genetic drift, and gene flow. Mutations introduce variation. Selection favors traits that improve survival. Drift and flow shuffle genes across generations. Together, they form the engine of change. What emerges is not perfection, but resilience, life's ability to endure in endless forms. Charles Darwin called it descent with modification, but in truth, it's more like nature's poetry written in DNA. That DNA, the blueprint of life, is both fragile and eternal. It carries the story of billions of ancestors, written in 4 letters: A, T, C, and G. Every human shares about 99.9% of this code with every other, yet that tiny fraction of difference gives rise to all the diversity we see. Inside you, ancient genes whisper from deep time, fragments inherited from fish, reptiles, and early mammals. You are, quite literally, a mosaic of the past, walking proof that life remembers. Evolution also shows that extinction is not failure, but transformation. Over 99% of all species that have ever lived are now gone, yet their disappearance made room for new life. The fossil record reads like a symphony, crescendos of creation followed by silences of loss, then renewed bursts of diversity. Even mass extinctions, devastating as they were, cleared the way for innovation. Without the asteroid that ended the dinosaurs, humans might never have emerged at all. Modern science continues to uncover new chapters in this story. Genetic research reveals connections between all living beings, from bacteria to blue whales. The study of epigenetics shows that genes can switch on or off based on environment, linking behavior and evolution more closely than ever before. Meanwhile, advances in synthetic biology allow scientists to edit DNA, effectively guiding evolution itself. It's both exhilarating and sobering. The same process that once shaped us unconsciously is now within our hands. In this grand perspective, evolution is not just a biological process. It's a story of adaptation, creativity, and endurance. It tells us that life is not fragile but tenacious, not static but ever-changing. From single-celled beginnings to thinking beings, evolution is the thread connecting every living thing. And as you read this, the story continues. Somewhere in the deep sea, a new organism is evolving. Somewhere in the soil, a microbe is mutating into a new form. Evolution never stops. It simply waits for the next challenge, the next opportunity, the next spark of life to push forward. We, too, are part of that flow, not its end, but one fleeting moment in its infinite journey. Every living being on Earth, from the simplest microbe to the most complex human, carries a cosmic inheritance. We are not separate from the universe, we are born of it. The iron in our blood, the calcium in our bones, the carbon in our cells, all were forged in the hearts of ancient stars. Billions of years ago, those stars lived, burned, and died in spectacular explosions called supernovae, scattering their elements across space. From that stardust, planets formed. And on one small blue planet orbiting an ordinary star, life began. Evolution is not just a biological story, it's a cosmic one. To say that we are made of stardust isn't poetry, it's physics. When massive stars reach the end of their lives, nuclear fusion in their cores can no longer sustain them. They collapse, releasing unimaginable energy, fusing heavier elements in a final burst of brilliance. Those elements, carbon, oxygen, nitrogen, drift through the galaxy, mixing with interstellar gas and dust. Eventually, gravity gathers that material into new stars, new planets, and new possibilities. Every breath you take contains atoms that once glowed in a sun long dead. You are, quite literally, the universe becoming aware of itself. Once Earth cooled and oceans formed, chemistry began its slow transformation into biology. Simple compounds like methane and ammonia reacted under lightning and ultraviolet light, creating amino acids, the building blocks of life. Experiments like the Miller-Urey experiment in the 1950s recreated these early conditions, proving that life's ingredients can form naturally. But how those molecules assembled into the first self-replicating cells remains one of science's greatest mysteries. Some theories suggest life began near hydrothermal vents, where heat and minerals provided the perfect environment for complex reactions. Others imagine it arriving from space, carried by comets or meteorites, a theory known as panspermia. However it began, life quickly evolved beyond chemistry. Single-celled organisms developed membranes, internal structures, and the ability to use energy efficiently. Over billions of years, these microscopic pioneers became architects of ecosystems. Photosynthetic bacteria filled the atmosphere with oxygen, while early predators introduced the balance of survival and competition. Evolution was no longer just about endurance. It became a story of interaction, of life shaping life. As organisms grew more complex, new challenges emerged. Senses evolved to navigate the environment: sight, smell, touch, hearing. Nerves formed pathways for information, allowing creatures to respond faster than chemical reactions could. Over time, brains appeared, small clusters of neurons that gave animals the power to remember, learn, and plan. From those primitive nervous systems emerged the foundation for consciousness itself. Life, once blind chemistry, began to perceive the world around it. The path from single cells to sentient beings was not linear, but layered with innovation and catastrophe. The rise of multicellular life allowed for specialization. Some cells for movement, others for digestion, others for thought. Complex organisms flourished, from trilobites to amphibians to mammals. Yet at least 5 mass extinctions nearly erased everything. Each time, life began again, evolving into forms more adaptive and aware. It was as if the universe itself refused to surrender, continuously reinventing consciousness through the lens of evolution. When primates appeared, the leap towards sentience accelerated. Opposable thumbs gave precision, but it was the expansion of the neocortex, the brain's outer layer, that changed everything. It enabled reasoning, empathy, and language. The ability to imagine the future and remember the past gave rise to culture, art, and morality. When humans began painting caves, building tools, and telling stories, they weren't just surviving. They were expressing awareness. The universe had found a way to observe itself through human eyes and describe what it saw. Sentience, the ability to feel and be aware, represents evolution's most extraordinary achievement. But it's not unique to humans. Many animals exhibit signs of consciousness. Elephants mourn their dead. Dolphins recognize themselves in mirrors, and crows use tools with remarkable intelligence. Sentience, it seems, isn't a single spark, but a spectrum, a gradual unfolding of awareness across species. In this way, humanity is not separate from nature's story. We are simply one of its latest verses. Yet with awareness comes burden. To be sentient is to know mortality, to realize that existence is temporary. This realization shaped civilization itself. Religion, philosophy, and science all stem from humanity's attempt to make sense of life and death. The same brain that evolved to hunt and gather now contemplates infinity, asking questions evolution never needed to answer. Why are we here? What happens after? Are we alone in the cosmos? These questions are the echoes of our biology meeting our awareness, instincts fused with imagination. Modern science continues to reveal how deeply our minds remain tied to the stars. Neurons communicate using electrical signals, just as lightning arcs through the sky. The patterns of galaxies and neural networks follow similar fractal geometries. Even the ratio of matter in the universe mirrors the ratio of connections in the human brain. These parallels remind us that consciousness isn't an anomaly. It may be a natural expression of complexity, the cosmos thinking in patterns, whether through stars or synapses. Some scientists and philosophers go further, suggesting that consciousness may not have emerged from matter, but may instead be a fundamental property of the universe, like space or gravity. This idea, called panpsychism, imagines awareness as woven into the fabric of reality itself. From atoms to galaxies, everything may possess a sliver of perception, a faint echo of being. If true, evolution didn't create consciousness. It merely refined it, allowing it to look back and recognize itself. And yet, even as we ponder our cosmic origins, we must face an uncomfortable truth. Evolution has no final goal. It doesn't strive for perfection or intelligence. It only favors what survives. Humanity, for all its brilliance, is just one branch in an infinite, ongoing experiment. We may think of ourselves as evolution's pinnacle, but the story isn't finished. It never will be. Life will continue to adapt, to change, to evolve long after we're gone. Perhaps one day, new beings, organic or synthetic, will inherit our world, carrying forward the spark we inherited from the stars. Still, there's beauty in knowing our temporary place in this vast continuum. The atoms that once belonged to ancient stars now form the thoughts reading these words. Every heartbeat is powered by the same energy that fuels suns. We are not separate from the cosmos. We are the cosmos, conscious and fleeting, marveling at itself. From stardust to sentience, the journey of life is both humbling and transcendent. It reminds us that existence is not an accident, but a miracle of persistence and transformation. In every breath, in every thought, the universe remembers its own origins. And perhaps, in moments of wonder and awareness, when we look up at the night sky and feel a quiet recognition, the stars are looking back, seeing themselves reflected in us. Every feeling you've ever had, love, fear, joy, sorrow, isn't magic. It's chemistry. Yet knowing that doesn't make it any less mysterious. Within the human body, a complex orchestra of molecules plays endlessly, producing the melodies we call emotions. Every flutter of the heart, every rush of excitement, every wave of calm has a chemical signature. And though these reactions happen invisibly, they shape our lives more than anything else. The chemistry of emotion is the bridge between the physical and the intangible, where molecules become meaning. At the heart of this process are neurotransmitters, chemical messengers that carry signals between neurons. Think of them as nature's language, allowing billions of brain cells to communicate. When you feel happy, frightened, or in love, it's because certain neurotransmitters surge or recede, shifting your state of mind in milliseconds. One of the most famous is dopamine, often called the reward chemical. When you accomplish something, whether it's finishing a task, eating your favorite food, or receiving praise, dopamine floods your system, producing pleasure and motivation. It's the brain's way of saying, "Do that again." But dopamine is a double-edged sword. Too little, and life feels dull, unmotivated, flat. Too much, and you chase stimulation endlessly through work, social media, or addiction. The same molecule that fuels creativity also drives obsession. It's not that dopamine makes you happy, it makes you want happiness, a subtle but powerful distinction. Then there's serotonin, the molecule of balance and well-being. It regulates mood, appetite, and sleep. Low serotonin levels are often linked to depression, anxiety, and irritability. Unlike dopamine's quick bursts of excitement, serotonin works more like a steady background rhythm, maintaining emotional stability. It's the chemical that allows us to feel calm, safe, and connected to the world. Interestingly, about 90% of serotonin is produced in the gut, not the brain, showing just how deeply our emotions are tied to our physical health. Oxytocin, sometimes called the love hormone, is released during touch, bonding, and intimacy. It's what helps mothers connect to newborns, and lovers feel close after an embrace. Oxytocin builds trust and empathy, literally changing how we perceive others. Yet it also highlights emotions' complexity. While it encourages bonding within a group, it can increase defensiveness toward outsiders. In other words, the same chemical that fuels love can also reinforce division. Emotion, like nature, rarely acts in simple absolutes. Adrenaline and cortisol, on the other hand, govern fear and stress. When danger appears, real or imagined, the brain's amygdala signals the adrenal glands to flood the body with these hormones. Heart rate rises, pupils dilate, senses sharpen. The fight-or-flight response engages. This ancient system evolved to keep us alive, but in the modern world, it often misfires. Deadlines, arguments, and notifications can trigger the same reaction as predators once did. Chronic stress leaves cortisol levels high, wearing down the body and mind. It's a reminder that our ancient chemistry hasn't yet caught up with our digital lives. The chemistry of emotion also explains why love feels like both an addiction and a sanctuary. Falling in love releases a potent cocktail of dopamine, oxytocin, and norepinephrine, flooding the brain with euphoria. The limbic system, our emotional core, lights up like a beacon. Rational thought diminishes as reward circuits take over, focusing entirely on the beloved. Over time, the initial rush fades, replaced by oxytocin-driven bonding and serotonin's quiet stability. Love, chemically speaking, evolves from obsession to attachment. And in that transition lies the secret to lasting connection, a balance between excitement and comfort. Emotion doesn't just happen in the brain. It ripples through the entire body. When you feel fear, your muscles tense, your stomach tightens, your skin cools. When you feel joy, your heartbeat steadies, your breath deepens, and your body relaxes. These physical sensations feed back into the brain, amplifying emotion. This feedback loop, known as the James Lang theory, suggests that we don't just cry because we're sad. We may feel sad because we cry. Emotion, then, is both cause and effect, thought and sensation intertwined. Another remarkable aspect of emotional chemistry is its adaptability. The brain learns emotional patterns over time. Each reaction you have strengthens certain neural pathways, a process known as emotional conditioning. That's why memories tied to emotion feel so vivid. The same chemicals that trigger feelings also tag memories for importance, ensuring that we remember not just what happened, but how it felt. In evolutionary terms, this made perfect sense. Remembering danger kept our ancestors alive, but it also explains why trauma can linger long after the moment has passed. The chemistry of fear burns deep. The interplay of emotion and memory also gives rise to nostalgia, a uniquely human experience. When we recall moments of joy tinged with loss, the brain releases a mix of dopamine and oxytocin, creating warmth and sadness at once. It's a chemical paradox, pain and pleasure coexisting. Nostalgia reminds us that emotions aren't simple switches, but complex symphonies of chemistry and meaning. Even creativity has a biochemical rhythm. Studies show that bursts of dopamine enhance divergent thinking, the ability to connect ideas in new ways. Serotonin and endorphins then help sustain focus and satisfaction during creation. That's why inspiration often feels like electricity, followed by calm, a natural cycle of chemical surges and restoration. The act of creating, in this sense, is emotional self-regulation through expression. Perhaps most fascinating is the link between the mind and the immune system. Emotions influence health at a molecular level. Chronic stress suppresses immune function, while joy, laughter, and connection release endorphins and antibodies that strengthen it. Even brief moments of happiness can alter gene expression, turning on pathways associated with healing. The chemistry of emotion doesn't just shape how we feel, it shapes how we live. Modern science continues to uncover how emotion defines our humanity. While artificial intelligence may mimic thought, it cannot yet simulate the biochemical tapestry that gives thought meaning. Every decision, belief, and dream you've ever had has been filtered through emotion, through molecules evolved to guide survival, yet capable of creating art, compassion, and love. So, the next time you feel your heart race or your chest tighten, remember, your body is speaking in the language of chemistry. Each emotion is a message, a molecular echo of your experience. And within those reactions lies the ancient intelligence of evolution itself, reminding you that to feel is to be alive, and that even the smallest molecule can carry the weight of an entire universe of meaning. Every thought we have passes through an emotional lens, whether we notice it or not. Feelings don't just color our decisions, they create them. We like to think of ourselves as logical beings who occasionally feel, but neuroscience reveals the opposite. We are emotional beings who sometimes think. The chemistry of emotion doesn't simply react to life, It builds the architecture of the mind itself. From memory to morality, creativity to consciousness, every corner of the brain is sculpted by the invisible hands of feeling. Deep within the brain lies the limbic system, the ancient emotional core that predates logic. It includes the amygdala, the hippocampus, and the hypothalamus, regions responsible for processing emotion, storing memory, and regulating hormones. The amygdala acts like a sentry, scanning every experience for danger or reward. When it detects threat, it triggers a cascade of chemical reactions. Adrenaline surges, muscles tense, and thoughts narrow to survival. But when it senses safety, it releases serotonin and oxytocin, opening the mind to trust, empathy, and learning. Emotion, in this sense, is not the opposite of reason. It's the foundation of it. Psychologist Antonio Damasio demonstrated this in a famous case study. A patient who suffered damage to his emotional centers could still think rationally, but he couldn't make decisions. Faced with simple choices, like what to eat or when to schedule an appointment, he was paralyzed by indecision. Without emotion, logic had no direction. It was feeling, not reasoning, that gave his choices meaning. This discovery reshaped how scientists understand the mind. Emotion doesn't cloud judgment. It guides it. The hippocampus, meanwhile, binds emotion to memory. Events that stir strong feelings, whether joy or trauma, are encoded more deeply than neutral ones. That's why you can vividly recall where you were during life-changing moments, but forget what you ate yesterday. Emotion tells the brain, "This matters, remember it." The neurotransmitters involved, particularly norepinephrine and cortisol, act like highlighters for memory formation. They ensure that moments of emotional intensity stay with us, shaping who we become. But feelings don't only define what we remember, they influence how we remember. Each time you recall a memory, your current mood subtly rewrites it. Happiness softens pain, sorrow amplifies loss. Over time, this emotional editing creates the stories we tell ourselves about who we are, what we've overcome, and what we value. In this way, feelings are not just experiences, but authors, constantly revising the autobiography of the mind. The mind's architecture also depends on emotional connection. Human infants, for instance, are born neurologically unfinished. Their brains rely on emotional interaction, touch, voice, eye contact, to grow properly. The hormone oxytocin floods the infant's brain during bonding, strengthening neural pathways that regulate trust and empathy. Without love or connection, those pathways can weaken, leading to emotional difficulties later in life. Emotion literally builds the brain, wire by wire, connection by connection. Even creativity is driven by feeling. Emotion fuels imagination by breaking boundaries and connecting distant ideas. When artists paint, musicians compose, or writers dream, they're translating emotion into structure, turning chemistry into beauty. Brain scans reveal that during creative flow, regions involved in emotion and reasoning synchronize, blending logic and intuition. Dopamine spikes in these moments, rewarding risk and discovery. The result is not just art, but innovation. Proof that feeling is the spark behind invention. Yet emotions can also distort perception. When fear dominates, the amygdala hijacks the brain, suppressing the prefrontal cortex, the seat of logic and foresight. This amygdala hijack explains why anger leads to rash choices, why panic freezes action, and why stress narrows perspective. Chronic emotional overload reshapes neural circuits, making the brain more reactive and less reflective. Over time, this can lead to anxiety, depression, or burnout, not as signs of weakness, but as byproducts of an overstimulated emotional system. Fortunately, the mind is resilient. Through emotional regulation, we can reshape how feelings influence thought. Practices like meditation, deep breathing, and mindfulness strengthen the connection between the emotional and rational centers of the brain. Studies show that consistent mindfulness reduces amygdala activity and increases the thickness of the prefrontal cortex, a literal rewiring of emotions' influence. In essence, we can teach the brain to feel without being ruled by feeling. Our moral sense, too, emerges from emotion. Empathy, guilt, compassion. These are not abstract virtues, but biochemical realities. When we witness kindness, the brain releases oxytocin and serotonin, reinforcing prosocial behavior. When we see suffering, the anterior insular and cingulate cortex activate, creating a visceral response to another's pain. Morality, then, isn't just taught, it's felt. The roots of ethics lie in chemistry, evolved to keep social species like us connected and cooperative. One of emotion's most fascinating powers is its ability to create placebo effects, real physical changes driven by belief. When people expect healing, the brain releases endorphins and dopamine, triggering genuine improvements in pain and mood. Expectation becomes biology, belief becomes medicine. This intertwining of mind and body shows that emotion isn't separate from physiology. It is physiology, just expressed through feeling. Even time itself is filtered through emotion. When we are afraid, moments stretch. When we're joyful, they fly. This happens because the amygdala and prefrontal cortex distort how we process temporal information. Emotion can make minutes feel like hours or years pass in a blink. Memory then becomes uneven, dense where we feel deeply, sparse where we don't. The richness of life is measured not by duration, but by intensity of emotion. In relationships, emotions act as invisible bridges between minds. Mirror neurons, brain cells that fire both when we act and when we see others act, allow us to feel what others feel. This neural empathy lets us share joy, sadness, and fear without words. When someone smiles at you, your brain mirrors their happiness chemically, releasing the same feel-good neurotransmitters. Emotion, therefore, is not confined within us. It's contagious, spreading through gestures, tones, and even silence. All these interactions show that the mind isn't a machine of reason, but a living landscape shaped by feeling. Our ideas, choices, and beliefs are carved by the emotional currents that flow beneath thought. Even scientific breakthroughs often begin with awe, an emotion that fuels curiosity and discovery. Emotion doesn't just accompany thought, it creates it. And perhaps that's what makes emotion so profoundly human. It binds the mechanical to the meaningful, turning electrical impulses into stories, data into dreams. The chemistry of feeling doesn't diminish our experience, it deepens it. It reminds us that logic alone cannot explain beauty, compassion, or hope. The mind may think in words, but the heart speaks in chemistry, and together they write the narrative of what it means to be alive. In the end, emotion is not weakness. It's wisdom written in biology. It's evolution's way of teaching the mind how to care, to connect, and to remember. The next time you feel a surge of joy, anger, or love, don't resist it. Listen. That feeling is your mind speaking its truest language, reminding you that to be human is to feel, and to feel deeply is to truly live. For all our progress, our telescopes peering across galaxies, our microscopes exploring the fabric of atoms, humanity still stands in the fog of the unknown. We are a species that maps the stars yet cannot fully map the mind. That splits the atom yet cannot explain consciousness. That understands evolution yet still wonders why it happened at all. The more we learn, the more we realize how much remains unseen. The limits of human knowledge are not barriers. They are horizons, ever expanding, always just beyond reach. From the beginning, knowledge has been our greatest pursuit and our greatest illusion. Early humans looked up at lightning and called it divine anger. Today we call it electricity. We once thought disease came from curses. Now we know it comes from microbes. Each discovery replaces mystery with understanding, yet beneath every answer lies a new question. The universe seems designed not for completion, but for endless curiosity. Every explanation deepens the mystery rather than ends it. One of the most profound limits we face is our perception. Our senses, though powerful, are narrow filters through which we interpret reality. We see only a sliver of the electromagnetic spectrum, hear a fraction of the frequencies that exist, and feel time in one direction only. There may be dimensions of existence all around us, sounds, colors, forces, that our biology simply can't detect. Instruments like telescopes and particle accelerators extend our reach, but even they can't reveal what lies outside the bounds of measurement. In this way, the universe is both infinite and invisible, hiding more than it shows. Physics, for all its elegance, runs into paradoxes that hint at the edges of comprehension. Quantum mechanics and general relativity, two of the most successful theories in science, cannot yet be reconciled. One governs the subatomic world, where particles behave like waves and probabilities. The other governs the cosmic, where gravity bends space and time. Together, they describe everything, except each other. The search for a theory of everything remains unfinished, a reminder that even our best models are incomplete. Then there's the cosmic frontier, the vastness beyond our telescopes. We've mapped billions of galaxies, yet what we see accounts for less than 5% of the universe. The rest is dark matter and dark energy, invisible forces that shape everything yet defy direct detection. We don't know what they are, only that they exist. Dark matter holds galaxies together. Dark energy pushes them apart. Their balance determines the fate of the cosmos, yet their nature remains one of science's deepest mysteries. In essence, most of the universe is made of something we cannot see, touch, or even describe. Our limitations extend inward as well. The human brain, capable of understanding the stars, struggles to understand itself. Neuroscience has mapped thousands of connections, identified neurotransmitters, and tracked electrical impulses. Yet the hard problem of consciousness remains unsolved. How does the physical brain produce subjective experience? How does chemistry become thought? Even as artificial intelligence mimics reasoning, the essence of awareness eludes definition. The mind remains both the tool and the mystery of knowledge. The limits of knowledge aren't only scientific, they're also philosophical. Can we ever truly know what reality is, or do we only perceive a filtered version of it? The philosopher Immanuel Kant argued that the world as we experience it, the phenomenal world, is shaped by the structure of our minds, and that the noumenal world, reality as it truly is, may be forever beyond comprehension. Modern physics echoes this. The act of observing something can change it, as seen in the quantum observer effect. In other words, the universe doesn't just exist independently, it interacts with our perception. Reality might depend on the observer, and that means total objectivity may be impossible. Time itself poses another limit. We experience it as a steady flow, Yet Einstein's relativity shows it's elastic, stretching and warping with gravity and speed. Near a black hole, time slows to a crawl. At the speed of light, it stops altogether. Our minds, bound by linear experience, can't truly imagine non-linear time, existence where past, present, and future coexist. Some physicists even propose that time might not exist fundamentally, but rather emerges from deeper physical laws. If that's true, then our most basic sense of reality, the passing of moments, is an illusion. Even mathematics, often considered the purest form of truth, reveals its boundaries. In 1931, mathematician Kurt Gödel proved that any consistent mathematical system will contain truths that cannot be proven within its own rules. This discovery, known as Gödel's incompleteness theorem, shattered the dream of a perfectly logical universe. It means there will always be facts beyond proof, truths beyond reason. Knowledge by nature is incomplete, not because we fail, but because the universe itself contains unprovable mysteries. And what about human understanding itself? Our brains evolved not to comprehend the universe, but to survive in it. We see patterns, make predictions, and create stories, not because they're always accurate, but because they help us navigate uncertainty. Our tendency to oversimplify, to anthropomorphize, to believe in narrative rather than randomness is a cognitive adaptation. It allows creativity and empathy, but it also blinds us. We see meaning where there may be none, and we miss meaning where it hides in plain sight. Technology may help us push those limits, but even our machines inherit our biases. Artificial intelligence, for all its power, learns from human data, our language, assumptions, and flaws. It may process information faster, but it doesn't necessarily see deeper. As knowledge expands, so do its blind spots. The more we illuminate, the longer the shadows become. Still, the limits of knowledge are not failures. They are invitations. Each unanswered question drives progress. The fact that we don't know what consciousness is, or what dark matter consists of, or what existed before the Big Bang, doesn't weaken science. It defines it. Curiosity thrives at the edge of understanding. The unknown is not a void, but a frontier, the place where imagination meets discovery. There's a humility that comes with realizing how little we truly know. For all our telescopes and theories, we remain a young species on a small planet, orbiting an ordinary star in one galaxy among trillions. Yet, from this tiny point in the cosmos, we ask questions that stretch across eternity. That act, to wonder, to seek, to imagine, may be the most extraordinary form of knowledge there is. So perhaps the real limit of human understanding isn't ignorance but arrogance, the belief that we can ever know it all. The universe is vast, not to mock our smallness, but to remind us that discovery is endless. To reach the horizon of knowledge is to find another horizon waiting. And maybe in that endless pursuit we find meaning not in what we know, but in our eternal desire to keep learning. For all its brilliance, science is still a work in progress, a candle flickering in the vast darkness of the unknown. Each century brings answers, yes, but also deeper mysteries. Some are questions of scale, too small, too vast, or too abstract for our instruments to grasp. Others strike at the heart of existence itself. Why does the universe exist? What is consciousness? Are we alone? These aren't failures of knowledge, but glimpses of its horizon, the unsolved riddles that keep curiosity alive. Perhaps the greatest mystery of all is the origin of the universe. The Big Bang theory tells us that everything, space, time, matter, and energy, began roughly 13.8 billion years ago from a point of infinite density. But what came before it? If time itself began at the Big Bang, then before may not even exist. Some theories suggest the universe could be cyclic, expanding and contracting endlessly. Others propose the multiverse, where our cosmos is just one bubble among infinite others. Yet despite decades of research, no one knows for certain why there is something instead of nothing. The question remains haunting and profound. What lit the spark of existence? Equally perplexing is the nature of dark matter and dark energy. We can't see or touch them, but their fingerprints are everywhere. Dark matter acts like an invisible scaffolding, holding galaxies together with its gravitational pull. Dark energy, on the other hand, pushes them apart, accelerating cosmic expansion. Together, they make up about 95% of the universe, yet we know almost nothing about them. Every telescope, every experiment searching for their identity returns silence. Whatever they are, they hold the secret to the universe's ultimate fate, whether it will expand forever, freeze, collapse, or transform into something entirely new. Then there's the enigma of time. We move through it in one direction, from past to future, but the laws of physics don't require this arrow. At the quantum level, particles can move forward or backward through time with equal ease. So why does time flow? Why do we remember the past, but not the future? Some scientists think it's tied to entropy, the universe's gradual slide toward disorder. Others believe time may be an illusion, an emergent property of deeper physical laws. Whatever the truth, our understanding of time remains as fragile as sand slipping through our hands. Even closer to home, we face the unfathomable mystery of consciousness. How does the brain, made of atoms and electricity, produce thought, emotion, and awareness? What does it mean to experience something? To see red, to feel love, to dream? Neuroscientists can map the activity of neurons, but not the essence of experience itself. Some propose that consciousness arises from complex information processing. Others think it's fundamental, woven into the universe like space and energy. Until we can explain awareness, we can't fully explain ourselves. Another puzzle lies within quantum mechanics, the science of the very small. Subatomic particles don't behave like solid objects, but like probabilities, existing in multiple states at once until observed, a phenomenon known as superposition. The act of observation collapses those possibilities into one outcome, raising a chilling question. Does reality depend on being observed? And if so, by whom? This intersection of physics and philosophy blurs the line between matter and mind, suggesting that consciousness and the cosmos may be more intertwined than we dare to imagine. The question of life beyond Earth also lingers in uncertainty. With billions of stars in billions of galaxies, it seems impossible that we're alone. Yet, after decades of searching, we found no clear evidence of extraterrestrial life. This contradiction is known as the Fermi paradox. If intelligent civilizations are common, where are they? Some believe advanced species may be too distant or too unlike us to recognize. Others fear they may have risen and fallen long before we arrived. The silence of the universe could be a warning or a promise that we are its rarest creation. Even on Earth, mysteries abound. We don't fully understand how life began. We can recreate its building blocks, but not the leap from chemistry to biology, from molecules to metabolism. The transition from non-living matter to the first cell remains one of the greatest unsolved questions in science. Did it happen in the ocean's depths, on volcanic shores, or in icy comets. Each theory is compelling, yet incomplete. Somewhere, perhaps in a drop of primordial water, nature performed its first act of creation, and we still can't explain how. Then there's the nature of reality itself. Quantum entanglement shows that particles can affect one another instantly, even across galaxies, a phenomenon Einstein famously called spooky action at a distance. This defies classical physics, suggesting that space and time might not be as separate as we believe. Some physicists think reality may be holographic, that the three-dimensional universe is an illusion projected from information stored on a two-dimensional surface. If true, then existence as we experience it could be a kind of cosmic simulation. Which leads to another unsettling question: could we ourselves be living in one? Modern technology also confronts mysteries we didn't expect. Artificial intelligence, for example, has begun generating language, art, and insight that even its creators can't fully explain. These systems operate through complex layers of computation, forming outputs that seem intuitive, almost creative. Yet no one completely understands how they make their decisions. This black box problem in AI mirrors the mystery of consciousness itself, intelligence without understanding, thought without awareness. Are we perhaps building mirrors that reflect mysteries we haven't yet solved in ourselves? Even biology still hides secrets. The placebo effect, for instance, shows that belief alone can trigger healing, altering brain chemistry and immune function without medicine. We don't yet understand how mind and body communicate so intimately. Similarly, death, the moment consciousness ends, remains an enigma. Science can describe what happens to the body, but not where awareness goes. Some researchers studying near-death experiences find patterns of brain activity that persist seconds after the heart stops. Whether these are hallucinations or glimpses of something beyond, no one can say. Each of these mysteries reminds us that knowledge has boundaries, and that those boundaries shift as we explore them. What seems impossible today may become obvious tomorrow. The Earth was once flat, atoms indivisible, the heavens eternal. Each generation inherits the unknown, pushes it forward, and leaves new questions behind. But perhaps that's what makes science beautiful. It doesn't promise certainty, it promises searching. It's an act of humility, an acknowledgement that understanding the universe means forever reaching toward what lies beyond understanding. We may never solve every mystery, and maybe that's the point. The universe doesn't reveal itself all at once. It unfolds slowly, inviting curiosity. Each unanswered question keeps the flame of discovery alive. And as long as that flame burns, in our labs, our imaginations, our hearts, humanity will never stop wondering, because it's not the answers that define us, but the endless, beautiful pursuit of them. The story of the universe begins not with light, but with silence, an infinite stillness before time itself existed. Then, in an instant, everything changed. Space, energy, and matter burst into being, expanding faster than the speed of light in an event we call the Big Bang. It wasn't an explosion in space, it was the creation of space itself. Every atom, every star, every thought that would ever exist was compressed into a single point, smaller than a grain of sand. From that singularity came the cosmos, vast, beautiful, and still expanding more than 13.8 billion years later. The Big Bang didn't create order, it created potential. In its first fraction of a second, the universe was unimaginably hot, trillions of degrees, a soup of energy and particles colliding in chaos. But as it expanded, it cooled. Within minutes, protons and neutrons formed, binding together into the first atomic nuclei. Light itself couldn't escape this dense fog until 380,000 years later, when atoms finally stabilized and photons could travel freely. That ancient light, stretched by time, still fills the universe today as the cosmic microwave background radiation, a faint whisper from creation's dawn, glowing faintly in every direction. This radiation is one of the strongest clues we have about our origins. Detected in the 1960s, it revealed that the universe wasn't perfectly uniform. Tiny fluctuations in its temperature showed the seeds of structure, the faint imprints that would grow into galaxies, stars, and planets. Gravity slowly pulled matter together, forming clouds that collapsed into the first stars about 100 million years after the Big Bang. Those early stars were giants, short-lived, brilliant, and explosive. They forged the first heavy elements in their cores and scattered them through space when they died. Everything that exists today, from mountains to mines, is built from the ashes of those first suns. But what caused the Big Bang? That's the question that continues to baffle scientists. Some theories propose that our universe was born from quantum fluctuations, brief ripples in a pre-existing vacuum. Others suggest a multiverse where countless universes bubble up endlessly, each with its own laws of physics. In that view, our cosmos is just one drop in an infinite ocean of reality. Still, others imagine that time didn't begin at all, that the universe expands and contracts cyclically, breathing in and out over eternity. Each theory answers one question only to raise 10 more, revealing that even the act of creation remains partly hidden from us. One of the most intriguing ideas is cosmic inflation, a theory that proposes the universe expanded exponentially in its first trillionth of a second. This rapid stretching would explain why space looks so uniform on the largest scales and why distant regions appear identical despite never having interacted. Inflation smoothed the wrinkles of creation, turning chaos into symmetry. Yet no one knows what triggered it or why it stopped. The spark that set off the universe remains one of the greatest mysteries in science. As the cosmos grew, stars gathered into galaxies, galaxies into clusters, and clusters into webs stretching across billions of light years. Astronomers now call this vast pattern the cosmic web, a network of filaments where galaxies form like pearls on invisible strings. Between these structures lie immense voids, dark and silent, where almost nothing exists. The universe, it turns out, is not evenly filled, but shaped by contrast, light and dark, matter and emptiness, order and chaos. At the center of many galaxies, including our own Milky Way, lurk supermassive black holes, millions or billions of times heavier than the Sun. These cosmic enigmas warp space and time, consuming light itself. Paradoxically, they may also give life to galaxies, releasing energy that drives star formation. Some scientists believe black holes could hold clues to the universe's origin, perhaps even remnants of the earliest moments after the Big Bang. In their depths, where gravity and quantum physics collide, the laws of nature as we know them break down completely. Understanding black holes may one day reveal what existed before existence. The universe's expansion, once thought to be slowing, is actually speeding up. This discovery, made in the late 1990s, shocked cosmologists and led to the concept of dark energy, an unseen force pushing galaxies apart. No one knows what dark energy is, but it now dominates the cosmos, determining its future. If it continues accelerating, galaxies will drift so far apart that their light will never reach each other. Trillions of years from now, the universe may fade into cold isolation, a silent, endless expansion into darkness. Yet some theories suggest this isn't an end, but a transition, the prelude to a new beginning, another burst of creation beyond our comprehension. Even as we look backward, we're also looking inward. The particles that make up your body were born in that first fire. The hydrogen in your water, the carbon in your cells, the calcium in your bones, all trace their lineage to the Big Bang and the stars that followed. You are, quite literally, a continuation of the universe's unfolding story. Every human heartbeat is powered by atoms that once belonged to the earliest galaxies. In that sense, the question, where did we come from, is cosmic and personal at once. Modern observatories like the James Webb Space Telescope now peer across 13 billion years of light, capturing the faint glow of the first galaxies. Each image is a glimpse into the past, a time machine showing the universe as it was just after its birth. And still, the farther we look, the more mysterious it becomes. What lies beyond the edge of observation? Is there an outside to the universe, or is it infinite? Science may never know. What we do know is this: from the simplest particle to the grandest cluster of galaxies, everything is connected by the same laws, the same origins, the same cosmic breath. The Big Bang was not just a beginning. It was a transformation, a moment when possibility became reality. And as the universe continues to expand, we remain part of its story. Tiny fragments of starlight, wondering, questioning, and reaching toward the mystery that gave us life. Science often feels like something distant, a field of equations, telescopes, and test tubes. But it's quietly alive in every breath, every sound, every flicker of thought. The everyday world, though ordinary at a glance, is powered by invisible laws and ancient forces that have been in motion since the dawn of time. From the swirl of milk in coffee to the rhythm of your heartbeat, you're surrounded by quiet miracles. The universe doesn't just live in distant stars. It hums beneath your fingertips, disguised as routine. Take something as simple as breathing. Each inhale pulls in oxygen molecules that were born in stars billions of years ago. Those atoms drifted through interstellar dust before becoming part of Earth's air. When you breathe them in, your lungs don't just extract gas. They ignite a microscopic fire. Inside your cells, oxygen reacts with glucose, releasing energy in a process called cellular respiration. This chemical dance powers every heartbeat, thought, and movement. Without it, life would stop in seconds. You are, in a sense, a living flame, not burning in light, but glowing quietly within. Even sound, something as familiar as music or conversation, is pure physics. When you speak, air molecules vibrate in waves that travel through space, striking the tiny bones in another person's ear. Those bones, the malleus, incus, and stapes, amplify the vibration and send it to the inner ear, where microscopic hairs translate it into electrical signals. The brain then decodes those signals into meaning. Every word you've ever heard or spoken is a symphony of atoms moving through air, a dance of pressure and pattern that turns vibration into emotion. Light, too, is extraordinary in its simplicity. It travels 300,000 kilometers per second, the fastest thing in the universe, and yet it can be bent, slowed, or split into colors. Every sunrise, rainbow, or reflection on water is a manifestation of electromagnetic radiation, energy oscillating in waves. When you see color, you're witnessing light interacting with molecules. A red apple absorbs every wavelength except red, which it reflects back to your eyes. What you see isn't the apple's inherent color, it's your brain interpreting reflected light. The world, as we perceive it, is a mental painting crafted by the interplay between light and mind. Even the act of walking is a marvel of hidden science. Your muscles convert chemical energy into motion with astonishing efficiency, using principles of physics that engineers still study. When you move forward, each step generates a controlled fall. Gravity pulling you down, balance pushing you up. Your inner ear senses motion through fluid-filled canals that detect acceleration and orientation. The brain synchronizes it all, adjusting muscle tension in milliseconds to keep you upright. You don't just move, you orchestrate a complex biological ballet without even thinking about it. Then there's water, the most ordinary yet most miraculous substance on Earth. It's the only natural compound that exists in all three states, solid, liquid, and gas, within normal conditions. Its molecular structure gives it unique properties. It expands when frozen, allowing ice to float and protecting aquatic life during winter. Water dissolves more substances than any other liquid, earning it the title of the universal solvent. It carries nutrients, erodes mountains, and fuels storms. Every droplet in the rain, every tear, every ocean wave is part of a cycle billions of years old, one that connects all living things in an endless exchange. Even sleep, often seen as unproductive, is a deeply scientific necessity. While you rest, your brain organizes memories, repairs neural connections, and flushes out toxins through a process called the glymphatic system. Dreams, though still mysterious, appear to be the mind's way of processing emotion and creativity. During REM sleep, your brain becomes almost as active as when awake, replaying and reshaping experiences. Far from idleness, sleep is one of the most dynamic biological events. Proof that sometimes the most productive thing the body can do is rest. Gravity, too, works quietly behind the scenes, keeping your coffee in the cup, your feet on the floor, and the moon in orbit. Yet it's also one of the weakest known forces, so weak, in fact, that a small magnet can lift a paperclip against the pull of an entire planet. Scientists still don't fully understand gravity's true nature. Is it a force, as Newton described, or the curvature of space-time, as Einstein proposed? It may even be a byproduct of quantum entanglement. Whatever it is, gravity shapes every moment of your existence, from the fall of an apple to the spin of galaxies. Even emotion has its scientific rhythm. When you laugh, your brain floods with dopamine and endorphins, strengthening social bonds. When you're afraid, adrenaline surges, sharpening focus. Chemistry, not magic, makes love feel electric and heartbreak feel heavy. Yet understanding these reactions doesn't make them less profound. It only deepens the wonder. The realization that molecules can produce joy, nostalgia, courage. That a cluster of neurons firing in harmony can make you feel infinite. Consider taste and smell, the senses that make life vivid. When you savor a meal, receptors on your tongue detect sweet, salty, bitter, sour, and umami flavors, while your nose perceives thousands of scents. Together, they create what we call flavor, a multisensory illusion of chemistry. The smell of rain after drought, called petrichor, comes from oils released by soil bacteria. The sweetness of fruit is a biochemical invitation from plants, evolved to ensure their seeds spread. Even pleasure is part of the planet's survival code. Technology may seem modern, but it's built upon these same timeless principles. Your smartphone's touchscreen responds because of capacitive sensing, detecting changes in electrical charge when your finger touches glass. GPS satellites orbit Earth, constantly adjusting for time dilation caused by relativity. Every tap, swipe, and message you send travels across electromagnetic waves, the same kind that carry sunlight and radio. The devices we use daily are, in truth, modern expressions of ancient physics. Yet perhaps the most fascinating scientific phenomenon of all is life itself. The improbable emergence of order from chaos. Out of random atoms arose consciousness, curiosity, and compassion. The odds of you existing with your specific DNA, thoughts, and experiences are astronomically small, and yet here you are, breathing starlight, powered by invisible laws, made of the same matter as galaxies. Science isn't something distant or cold. It's the language the universe speaks when it whispers through the mundane. Every ordinary act, eating, dreaming, walking, is a small miracle of physics, chemistry, and biology working in perfect harmony. To live is to participate in the greatest experiment of all, existence itself. So the next time you sip your coffee, feel the breeze, or stare at the stars, remember, you're not just observing science. You are science, in motion, in thought, in being. The universe isn't out there. It's in you, unfolding one beautiful, mysterious moment at a time. Reality feels solid, dependable, the floor beneath your feet, the air you breathe, the sky above your head. Yet science keeps reminding us that what we perceive as real might only be a thin layer of something far stranger. The deeper we look, the less stable reality becomes. Matter dissolves into energy, time bends, and observation itself seems to shape existence. Every discovery about the universe peels back another illusion, revealing that the boundary between what is and what seems may be far blurrier than we ever imagined. At the atomic level, solidity is an illusion. Everything around you, the chair you sit on, your skin, the stars, is made almost entirely of empty space. The atoms that form your body are 99.999999% nothing. The electrons that orbit the nucleus don't behave like planets circling the sun. They exist in clouds of probability, sometimes acting like particles, sometimes like waves. They don't have definite positions until they're observed. This is the essence of quantum mechanics, and it shatters every intuitive idea of what reality should be. In the subatomic world, certainty doesn't exist, only possibility. The observer effect takes this even further. In countless experiments, particles behave differently when measured, as if they know they're being watched. The famous double-slit experiment demonstrated that light and matter can exist in multiple states simultaneously, until observation collapses those probabilities into one outcome. This raises a haunting question. Does consciousness play a role in shaping reality? If the act of observing changes what is real, then perhaps the universe isn't a fixed stage, but a kind of cosmic conversation between the observer and the observed. Philosophers have long wrestled with this. Is the world independent of our minds, or does our perception help create it? Some scientists, like proponents of quantum idealism, suggest that consciousness might be fundamental, that matter arises from awareness, not the other way around. Others argue for a more materialist view, that observation simply interacts with the physical laws of probability. Yet neither explanation fully satisfies. Reality seems to exist in a paradox, both external and participatory, objective and personal at once. Then there's the mystery of time, perhaps the most elusive feature of existence. We experience it as a steady flow from past to present to future, but physics doesn't require that direction. The equations of relativity work perfectly, whether time moves forward or backward. According to Einstein, time is woven into the fabric of space, forming a four-dimensional continuum called space-time. Gravity isn't a force pulling on objects, but the warping of this space-time by mass and energy. To a photon of light, time doesn't pass at all. Every moment of its journey, from emission to absorption, happens simultaneously. That means the linear flow of time we perceive may simply be a trick of human consciousness, an emergent property of how our brains process change. Our perception of the world is equally deceptive. The colors you see don't exist outside your mind. They're interpretations of light wavelengths created by your brain. The taste of chocolate, the sound of rain, the warmth of sunlight, all are sensory translations of energy reconstructed by neural chemistry. What you experience as reality is a virtual model your brain builds from limited data. In truth, we never experience the world directly, only our brain's version of it. Every second, billions of sensory signals are filtered, interpreted, and transformed into the illusion of a continuous world. This realization leads to unsettling but profound questions. If our brains create a model of reality, how do we know what's truly out there? Could the universe, as we experience it, be more of a projection than a physical space? Physicist David Bohm once suggested that the visible universe might be a holographic projection of deeper, hidden dimensions. The holographic principle, now explored in modern physics, proposes that all the information in our three-dimensional reality could be encoded on a two-dimensional surface, much like how a hologram projects depth from a flat image. If true, the entire cosmos, galaxies, stars, even consciousness, may be part of a vast cosmic illusion of depth. Even the concept of matter dissolves under scrutiny. According to quantum field theory, what we think of as particles are actually fluctuations in invisible fields that permeate space. Electrons, protons, and quarks aren't solid things, but temporary vibrations, energy expressing itself as matter. This means everything you see, touch, and feel is a kind of frozen music, energy oscillating in harmony. You are, in the most literal sense, a pattern of energy waves dancing in the fabric of the cosmos. At the largest scales, reality warps again. Near black holes, gravity becomes so intense that space and time twist together. If you fell into one, you'd never cross the event horizon in the eyes of an outside observer. Your image would freeze, fading into red light forever. But from your perspective, you'd fall freely, possibly entering a realm where time and space trade roles. Some physicists believe black holes could connect to other universes or dimensions, cosmic doorways to realities beyond our own. Whether that's true or not, they remain places where the laws of physics as we know them break down completely. The concept of parallel universes also blurs the edge of reality. In the many worlds interpretation of quantum mechanics, every possible outcome of every decision actually occurs in separate branching universes. In one, you're reading this sentence. In another, you stopped halfway. Every choice, every chance splits the universe infinitely. Though we can't yet test this, it raises the possibility that reality is not singular but endlessly multiplying, a vast cosmic tree of possibilities, each leaf a different version of existence. Even consciousness itself challenges our understanding of reality. Neuroscience can describe how neurons fire, how signals travel, how thoughts emerge, but it can't explain why we experience them subjectively. Why does matter think? Why do atoms in your brain produce awareness, while atoms in a rock do not? Some scientists argue that consciousness may be fundamental, a basic property of the universe, like gravity or charge. Others speculate that reality itself may be a grand act of awareness, the universe observing itself through us. If that's true, then perhaps reality isn't something separate from us. It's something we participate in creating. Every observation, every act of attention, every spark of curiosity might be shaping the very universe we seek to understand. In that sense, science and spirituality converge. Both are quests to uncover the mystery behind the illusion, to touch whatever lies beyond perception. So what is real? Maybe everything, maybe nothing. Or maybe reality is not a single answer, but a living question, one that keeps unfolding the more we explore. The edge of reality isn't a boundary we'll ever cross, but a mirror reflecting the infinite depth of our own awareness. The universe may be vast beyond comprehension, but the mind that perceives it is just as infinite. And somewhere, in that shared mystery between matter and meaning, reality quietly breathes, both within and beyond us. From the moment early humans first looked up at the night sky, we've been asking the same question. Why? Why are we here? Why does the universe exist? Why does it seem so impossibly vast, yet capable of producing something as delicate and self-aware as the human mind? Across time and culture, that question has echoed through temples, observatories, laboratories, and quiet rooms of thought. We build telescopes to peer outward, microscopes to look inward, and stories to make sense of both. Yet the more we learn, the deeper the mystery grows. Knowledge, it seems, is a horizon. The closer we move toward it, the farther it stretches away. Science, at its heart, is not about answers, but curiosity. It's a way of asking the universe who and what we are, using the language of evidence instead of faith. Every discovery, from fire to flight, DNA to quantum mechanics, has opened new doors while revealing new shadows. We've learned that Earth orbits the Sun, that the Sun is one star among billions, and that those stars are but grains of light in a universe of unimaginable size. But for all our progress, we're still children of the cosmos, holding a spark and calling it a torch. Consider how far we've come. Just a few centuries ago, the concept of germs was unknown. People thought disease came from bad air or curses. Today, we manipulate DNA, map the human brain, and explore planets millions of miles away. Yet for every solved mystery, a dozen new ones emerge. What is dark matter? What is dark energy? How does consciousness arise from matter? Why do the constants of physics seem perfectly tuned for life? These aren't trivial gaps in knowledge. They're reminders that understanding reality may be an infinite pursuit. The beauty of science is that it never claims finality. Every theory, no matter how elegant, is provisional, waiting to be tested, challenged, and refined. Newton's laws gave way to Einstein's relativity. Einstein's universe gave way to the quantum realm. Even now, the frontier is shifting. Artificial intelligence learns and creates in ways we barely comprehend. Quantum computers are rewriting what computation means. Genetic engineering blurs the line between natural and designed life. Each step forward transforms not just what we know, but who we are. Still, beneath the complexity, the essence of science remains simple. Curiosity married to humility. It's the recognition that we don't know everything, and that not knowing is what makes discovery possible. The endless quest for understanding isn't a flaw in human nature, it's our defining trait. It's what separates us from the mechanical and binds us to the cosmic. We are the universe, asking itself questions. Every act of wonder, every child staring at the stars, every researcher in a lab, every artist exploring beauty is part of that same eternal conversation. Philosophers often speak of the unknowable, but perhaps the unknowable is not a wall, it's a mirror. When we explore the world, we inevitably explore ourselves. The more we uncover about nature, the more it reflects our own mysteries, consciousness, morality, emotion, and meaning. We've learned that reality is not purely objective or subjective, but something in between. It's both the dance of particles and the experience of being. The scientist and the poet, it turns out, are searching for the same thing: connection. The quest also humbles us. We now know that our planet is just one of billions orbiting billions of suns. Yet out of this vastness came beings capable of love, art and reason, of naming the stars and longing to touch them. That alone is miraculous. The atoms in your body were born in ancient stars, the iron in your blood, the calcium in your bones, the oxygen in your lungs, all were forged in the hearts of dying suns and scattered through space before coalescing into you. You are the cosmos made conscious, the universe gazing back upon itself. And yet, for all its majesty, the universe doesn't offer easy answers. It gives us patterns and probabilities, but not purpose. That part we create. Meaning is not found in the equations or galaxies. It's woven through our connections, our creativity, our capacity to care. When we reach for understanding, we're doing more than exploring physics or biology. We're participating in the unfolding of something timeless, a story that began before stars and will continue long after they fade. Even if humanity someday solves the deepest mysteries, if we decode dark matter, unify quantum theory and relativity, or even simulate consciousness, there will still be questions left. What existed before existence? What is awareness made of? Why is there order at all instead of chaos? These aren't scientific puzzles alone. They are existential ones. And perhaps they're not meant to be solved, only contemplated. Like standing at the edge of an ocean, knowing you'll never drink it all but finding wonder in each wave. The endless quest for understanding is, in many ways, our greatest act of hope. It's proof that even in a universe that doesn't promise meaning, we create it anyway. It's in the astronomer mapping galaxies, the child asking why, the artist painting what can't be measured, the teacher passing down curiosity like a torch. The search itself is what makes life luminous. So as we close this exploration, through mysteries of matter, mind and cosmos, remember that curiosity is not a phase of youth, it's the pulse of existence. We were born to ask, to seek, to learn, and to dream. The universe may never hand us every answer, but perhaps it doesn't need to. The wonder lies in the reaching, not the arriving. And in that endless reaching, in the space between question and understanding, we find something sacred, the quiet realization that knowing is less important than wondering. The universe remains vast, strange, and beautifully unfinished, just like us. From the moment early humans first looked up at the night sky, we've been asking the same question. Why? Why are we here? Why does the universe exist? Why does it seem so impossibly vast, yet capable of producing something as delicate and self-aware as the human mind? Across time and culture, that question has echoed through temples, observatories, laboratories, and quiet rooms of thought. We build telescopes to peer outward, microscopes to look inward, and stories to make sense of both. Yet the more we learn, the deeper the mystery grows. Knowledge, it seems, is a horizon. The closer we move toward it, the farther it stretches away. Science, at its heart, is not about answers, but curiosity. It's a way of asking the universe who and what we are, using the language of evidence instead of faith. Every discovery, from fire to flight, DNA to quantum mechanics, has opened new doors while revealing new shadows. We've learned that Earth orbits the Sun, that the Sun is one star among billions, and that those stars are but grains of light in a universe of unimaginable size. But for all our progress, we are still children of the cosmos, holding a spark and calling it a torch. Consider how far we've come. Just a few centuries ago, the concept of germs was unknown. People thought disease came from bad air or curses. Today, we manipulate DNA, map the human brain, and explore planets millions of miles away. Yet for every solved mystery, a dozen new ones emerge. What is dark matter? What is dark energy? How does consciousness arise from matter? Why do the constants of physics seem perfectly tuned for life? These aren't trivial gaps in knowledge. They're reminders that understanding reality may be an infinite pursuit. The beauty of science is that it never claims finality. Every theory, no matter how elegant, is provisional, waiting to be tested, challenged, and refined. Newton's laws gave way to Einstein's relativity. Einstein's universe gave way to the quantum realm. Even now, the frontier is shifting. Artificial intelligence learns and creates in ways we barely comprehend. Quantum computers are rewriting what computation means. Genetic engineering blurs the line between natural and designed life. Each step forward transforms not just what we know, but who we are. Still, beneath the complexity, the essence of science remains simple: curiosity married to humility. It's the recognition that we don't know everything, and that not knowing is what makes discovery possible. The endless quest for understanding isn't a flaw in human nature. It's our defining trait. It's what separates us from the mechanical and binds us to the cosmic. We are the universe, asking itself questions. Every act of wonder, every child staring at the stars, every researcher in a lab, every artist exploring beauty, is part of that same eternal conversation. Philosophers often speak of the unknowable, but perhaps the unknowable is not a wall, it's a mirror. When we explore the world, we inevitably explore ourselves. The more we uncover about nature, the more it reflects our own mysteries, consciousness, morality, emotion, and meaning. We've learned that reality is not purely objective or subjective, but something in between. It's both the dance of particles and the experience of being. The scientist and the poet, it turns out, are searching for the same thing: connection. The quest also humbles us. We now know that our planet is just one of billions orbiting billions of suns. Yet out of this vastness came beings capable of love, art, and reason, of naming the stars and longing to touch them. That alone is miraculous. The atoms in your body were born in ancient stars. The iron in your blood, the calcium in your bones, the oxygen in your lungs, all were forged in the hearts of dying suns and scattered through space before coalescing into you. You are the cosmos made conscious, the universe gazing back upon itself. And yet, for all its majesty, the universe doesn't offer easy answers. It gives us patterns and probabilities, but not purpose. That part we create. Meaning is not found in the equations or galaxies. It's woven through our connections, our creativity, our capacity to care. When we reach for understanding, we're doing more than exploring physics or biology. We're participating in the unfolding of something timeless, a story that began before stars and will continue long after they fade. Even if humanity someday solves the deepest mysteries, if we decode dark matter, unify quantum theory and relativity, or even simulate consciousness, there will still be questions left. What existed before existence? What is awareness made of? Why is there order at all instead of chaos? These aren't scientific puzzles alone. They are existential ones. And perhaps they're not meant to be solved, only contemplated, like standing at the edge of an ocean, knowing you'll never drink it all but finding wonder in each wave. The endless quest for understanding is in many ways our greatest act of hope. It's proof that even in a universe that doesn't promise meaning, we create it anyway. It's in the astronomer mapping galaxies, the child asking why, the artist painting what can't be measured, the teacher passing down curiosity like a torch. The search itself is what makes life luminous. So as we close this exploration through mysteries of matter, mind, and cosmos, remember that curiosity is not a phase of youth. It's the pulse of existence. We were born to ask, to seek, to learn, and to dream. The universe may never hand us every answer, but perhaps it doesn't need to. The wonder lies in the reaching, not the arriving. And in that endless reaching, in the space between question and understanding, we find something sacred, the quiet realization that knowing is less important than wondering. The universe remains vast, strange, and beautifully unfinished, just like us.